I'm Joanne Browning. I'm the Dean of Engineering here at UTSA and part of the Network Coordination Office for NHERI, the Natural Hazards Engineering Research Infrastructure. And welcome to our virtual workshop for early career faculty and researchers. This is something that we have every year. Actually, we usually have it in person in San Antonio. But this year, of course, with COVID-19, we're moving to the online method. Now, this workshop today is made possible through a grant through the National Science Foundation. You can see our grant number there on the screen, and much thanks to our program manager, Dr. Joy Pauschke at NSF. So, and Joy is joining us today, and you'll hear from her later in the afternoon as well. So thank you so much, Dr. Pauschke, for being here with us. There we go. So again, this is an activity that we have every year with NHERI and through the Network Coordination Office. But this year we're doing it virtually. We wish you were here with us in San Antonio. It's a lovely day here, and as we do this in the future years, we hope that you'll look for invitations to join in person. Because normally when we're having this Summer Institute, which we're doing a virtual workshop this year, we have lots of time for collaboration, for meeting new people and learning a lot about the sites and how to put together successful proposals. So we really want you to think about joining us again in person in a future year. But quickly, I'd like to just introduce a couple of people to you. First of all, the PI for the Network Coordination Office for NHERI is Julio Ramirez, and he's joining us today as well. And he's at Purdue University, and so many thanks to him for helping to coordinate activities. Myself, so I'm here, and I'll be joining you throughout the day, especially just with this quick little introduction to get us started. But Dr. Karina Vielma, who's an assistant professor here at UTSA in engineering education, is really the one I think you've been corresponding with the most, and she will be leading us through most of the day and guiding us through the various presentations. And so please feel free to reach out to her with any questions you have today or in the future about our activities. And so just a little bit about NHERI to get us started here. I'm just going to give a quick 10-minute intro, and then we'll move into the real heart of the matter today when learning from the sites. First of all, our mission for NHERI is to enable research and educational advances that can contribute knowledge and innovation to improve the resilience of the civil infrastructure against earthquakes, tsunamis, windstorms, and storm surge. And our vision as the NCO, the Network Coordination Office, is to serve as the focal point and leader of a multi-hazards research community, which is focused on mitigating the impact of future earthquakes, windstorms, and related hazards. And the way we accomplish this through NHERI is through this collaboratory, this great wealth of expertise and facilities and resources that the community has access to help mitigate the impacts of these severe events. And so as you can see in our NHERI wheel here, there's a number of facilities that are available to you. And what's so great about today is that you're going to get to hear from each one of them and hear from experts at these sites that can tell you about their facilities, about their resources, and how your research can be enabled through these great resources. But I'm going to start today with us here just telling you a little bit about the Network Coordination Office, and I promise to keep this brief, just so you can get some bearings on how things are coordinated through our collaboratory. So here's our org chart, which I know is a little busy, but I also know that Karina has sent these slides out to you so you can study it later if you would like. But really, if you notice the color coding here, you can see that we have our institutional oversight, which is located at Purdue University. And then the Network Coordination Office itself is made of a number of individuals who put their time into helping coordinate activities through a number of ways. And I will be introducing you to some of those folks during this really brief presentation. So you'll know who to reach out to when you have a question about a particular area. But I also want to point out this lighter blue area, which is our Miri Governance, which I think is really important to everyone in the community. So we have what's called the NIAC, the Network Independent Advisory Council, and they do are formed by a number of leading researchers who are independent of the network and give us advice on how we can be more impactful with our activities. And then there's the NHERI Council, which is made up of the site PIs, so we have some internal governance that way. And then there's the user forum, which I really want to point out because a number of you could become involved with NHERI activities and have more of a direct say on day-to-day activities by getting involved in the user forum. And we did just complete the elections for those that are serving this year, but please be on the lookout in future years for ways that you can get involved, because this is made up of the people that use the resources of NHERI. And I want to point out one of our team members, Dr. Antonio Bobet at Purdue University, who serves as the leader of the user forum activities and helps to make sure that the NCO is coordinated with what the user forum is telling us. Now, you may be asking, well, then how do I get to these facilities? How do I get to these resources? And access to the facilities is coordinated through the NCO. So we have a centralized facility scheduling module that looks at all user time, both NSF supported and those that are non-NSF supported, for each experimental facility, including the rapid reconnaissance facility. And Dan Ziener on our team is the one that you would go to help coordinate those things, but you can find all of this information as well on Design Safe, and you will hear from them later today, but also in your introductory materials, you received links on how to get into Design Safe as well. And what kind of funding, you may ask? Well, it really can come in all different shades. So there's definitely the NSF, CMMI funding, but other directorates through NSF as well. So we really encourage you to look through all the opportunities for funding that could be used to solve these problems that exist around natural hazards. And of course, any other federal, state agencies, industrial funding, there's a lot of ways to be able to have access to the resources in NHERI. You may also be wondering, well, how do we know that we're making an impact on meaningful problems? How do we know that we are contributing to NHERI's overall goals and mission? Well, one way you can do that is to use our NHERI science plan as a resource. This is a plan that was developed with a very collaborative, interdisciplinary task group of folks, but also input from a number of places, including for other summer institutes we've had in the past, where we have people across all these different areas coming together and identifying where some of the big needs are within research. So I really want to encourage you to look back on this resource, which again is located on Design Safe, and to look for ideas, but also to see where your own ideas fit into this greater network and greater framework of activities that we are trying to solve to help mitigate these issues. And this activity has been led by a couple of our colleagues, Billy Edge at NC State and Tom Smith, who are both part of the NCO. Now, we also sent you another flyer when you registered for the Technology Transfer Committee. This committee has been designed to help take research results and find more immediate impact from those results. How do we get them into our everyday workplace so that we can see the impact of NHERI research on mitigating these hazards? And so they facilitate and speed the transfer of research results into active engineering practice. And this effort has been coordinated by our own Bill Holmes as an NAA member and also a structural engineer. And he has worked with this task group, this committee of over 20 individuals, mostly engineers, that have experience in design, but also this great experience and understanding of the complexities for transferring technology into real use, whether it's through design codes or design guidelines or other ways. So just a couple things I'd like you to consider with that flyer. First of all, if you are looking for advice on how to make impact with your research, please consider asking for a consultation with our Technology Transfer Committee. And again, this is located in the slides that you received, but it's also on the flyer that you received when you registered. And you just send an email to this group and they'd be happy to talk to you. Another one is that they have put together a white paper to help guide some of these ideas. And so if you go to Design Safe, and the link is there on your flyer, you can also find this resource that may be the best way for you to get started when you're writing your proposal and trying to think about how to make sure that you're making impact with your work. Now, this workshop, as well as other types of outreach, have been coordinated through the education and community outreach portions of our NCO. And our goal is to plan and drive activities to engage and expand the NHERI community. And we've been doing this in a number of ways. One is our REU program that happens every summer, except for this summer because of COVID-19. We're doing a sort of a virtual environment in its place this summer. But in the past, we've had anywhere from 30 to 33 students that are going to the various sites and being engaged and integrated into this really cutting edge research, learning and being trained on all the new types of equipment and new types of research methods that are there, and then returning to their home institutions and bringing that knowledge with them and looking to become graduate students themselves. And so please encourage your students at your locations to consider being part of our REU program next summer. It's really a fantastic experience. We also have the Summer Institute, which I mentioned, and this workshop is in place of it this year. But generally that's over 3 days where we have people from across disciplines working together in teams, developing research projects, working in tandem with NSF project managers and working with the sites and others, and really getting a lot of experience. So consider that applying for next year. And then there's a whole other wealth of resources available on Design Safe through our Learning Center that you should check out. But all of this is possible because of our Education and Community Outreach Committee. And as you can see on this slide, it is chaired and led by our own Karina Villalma. But you can see that we have representatives across the various sites as well as from the user forum. And everything we do has been designed by these people. They know what you need to be successful at their sites. They also are looking at what's coming out of the research at their sites and helping to make sure that that's transferred to you and that there's other ways for you to be engaged with it. And so a big thank you to all of our folks that have participated on the ECO committee and who have particularly designed today for you to make it most impactful and the best use of your time. So today, what's it look like? Well, we're going to have a series of presentations, as you saw, from our experts at the various sites with a break for question and answers in between, sets of 3 of these. And then we are going to top this off with a great presentation from Dr. Joy Pauschke on grant writing this afternoon. And then with an NSF awardee panel, which has been really successful in future years, and people have really appreciated having some advice and hearing from those that have received NSF funding in the past. Now tomorrow is reserved for individual meetings with site representatives and with our program manager, Dr. Joy Pauschke. I believe there are still some slots available, as I know for sure with the site personnel. And so you received this link when you registered, but you can still go to that link, and Karina Villalma will be fielding anybody that comes in today and seeing if there are any slots available for you to meet personally with someone tomorrow. Now, we really want you to make the most of the day. We know you're spending your time here with us and you're hoping to get particular things, but let us please offer some advice on how we think you can get the most out of today's activities. First of all, as we do with everything around the ECO work, we are working here to build community. And you, being a part of today's activities, are now part of our community. And we want you to feel that way. One way that you can really get engaged quickly is to visit the Padlet site that was created for this event and put some information about yourself up there. And as someone asks questions, or as you ask questions, or other comments are made, you can learn about each other and perhaps find a great collaborator for the future. So that's the second point. Ask questions, get involved today. Note all the available resources that you're learning about and potential collaborators, and then follow up and use those resources yourself, because I think you're gonna find that they can greatly enhance the research that you would do on your own. Also, you're going to learn about key elements for grant proposals today, and so please take advantage of that. Learn the details of the experimental facilities and the site resources that are available, and also training that they have so that you can follow up with that if it's a site that particularly perks your interest. And then gain strategies and knowledge from NSF today so that your proposals can be even more successful. And finally, I'd be remiss if I didn't tell you to please connect with us. My colleague, Cheryl Ann Blaine, who leads our communications efforts, has worked very hard with our other colleagues, Chris Thompson, Marty LaChance, and Lynn Holland, to provide ways for you to learn about research that's going on within our community. So please like us on Facebook and Twitter. Please join Design Safe at designsafe-ci.org so that you can get our monthly emails on what you've missed, but also our quarterly newsletters, and that you can be the most productive community member in NHERI. So with that, I want us to get started. So I'm going to turn it over to Karina so that she can introduce our first speaker. And again, please enjoy your day. Feel free to reach out to any of us at any time.
My name is Arindam Chaudhary. I'm the director and the PI of the Nihiri Wall of Wind facility at FIU, Miami. This is a picture of the facility. We have a 12-fan system to create hurricane winds. So we have these fans, as you can see, very high-powered fans, and we have a wind field cross-section of 20 feet by 14 feet, so we can do like large-scale and full-scale testing. We have a turntable to simulate the various directions of the wind. And the way that we are unique in our capabilities is like we can go up to category 5 hurricane wind speed, which is almost 160 miles per hour. And we can do like multi-scale testing in terms of full scale or large scale testing. We can also test structures to destruction. So we can study some of their failure modes of the structures and look at, cascading progressive damage. And we also have wind-driven rain simulations. So we can study water intrusion through buildings. And we do testing on buildings and other infrastructure systems as well. So these are some of the facilities that are included in our EF. So we have a control room, as you can see. We also have the turntable and the flow management devices to create the boundary layer. And we have a staging area where you can build your models. So we can entertain like various users, someone building their models in the staging area while someone doing their testing at the test section of the wall of wind. We also have the capability, a new capability of creating downburst winds. This is a small scale simulation. So not only we are doing the hurricane winds, but we are also adding to that non-synoptic downburst winds so we can compare the effects of hurricanes as well as downburst simulations on structures. So I'd like to just go through a few examples so you get to know like some of the very fundamental aspects of NHERI. So I have 4 points here about the Nihiri Vision. One is we want to predict the life cycle performance of civil infrastructure under natural hazards. We also want to reduce the future reliance on physical testing through computational modeling. And whatever research we do, we want to translate that research into innovative mitigation and strategies or technologies. And finally, our goal is to train an inclusive STEM workforce by educating teachers and students. So we want to integrate the research, education, and outreach. So I'm just going to go through these 4 with some examples. So the first one here is about the life cycle performance. In our facility, we can do system level testing. So you can see like this is a standing seam metal roof, which is showing the vibrations, and it can capture the failure modes. Like you can see some of the connections are failing at high winds, and you can kind of know the locations of those failures. So you can go back and redesign or retrofit the system. So this is like a system level performance of things that we can do. We also have the same thing for infrastructure, where this is a traffic signal system, and you're going to see like at certain wind speed, you can see instability setting in, causing failure, right? So again, this is an example of a system level testing where we can not only measure the loads and other wind effects, but we can also see like here you have a failure under an instability condition at a critical wind speed. We can capture these things at full scale, both buildings and infrastructure. About the reducing the reliance on physical testing, CFD modeling or any numerical modeling is very essential to reduce the reliance on physical testing. But to validate those technologies, we need some means. So we are happy to let you know that we have got an MRI award from NSF, in which we got a PIV system, particle image velocimetry system, in which we shoot, laser, and we can get images of the flow behind a structure. And that way you can have all the flow information at large scale, so you can go and validate your CFD modeling. So this is very good because this opens a new niche in fundamental fluid mechanics, and it can also propel transdisciplinary research between, you know, structural engineers, wind engineers, fluid mechanists, and things like that. About the innovation techniques, you can see like here, this is a technique that was developed at the Nihiri Wall of Wind about how to reduce wind load using turbines on the edge of the roof. At the same time, these turbines can create energy, wind generated energy, green energy. So this is a solution where you can kind of integrate both sustainability and resiliency. So on the left-hand picture, you can see the vortices and the scouring on the roof because of the wind uplift. On the right-hand picture, you can see the turbines and you don't see any scour. That means the wind load is reduced, but at the same time, we are producing power. So we can combat power outages during hurricanes. We had many of these power outages, and there is a real need to supply some power to the building during windstorms. About the integrating the research, education, and outreach, we have REU, RET programs. On the left-hand picture, you can see we have teachers who are building small wind tunnels. They come to our facility to participate on a research experience for teachers. And then of course, they work also with the RU students, which come on our site from the NHERI RU Summer program. They all learn hand in hand. And the users can also leverage these outreach things that we do so that they can also use some of this in their proposals. Based on all these research and educational aspects, we made significant impact, for which the AC has given us the Charles Pankow Award of Innovation, because we have opened the realm of research and education opportunities never before possible. So I want to take a couple of minutes to just go through some NSF proposal, competitive NSF proposal. And I know that Dr. Poshke is going to talk about this at length today, and that will be extremely helpful. But what I'd like to just emphasize that just remember that the National Science Foundation has the science in the middle. So you always have to think about the science when you write a proposal. And there is a linear progression of the logic. So once you have a knowledge gap in that science or an educational need, then your goal is to find a scientific objective or an educational objective to kind of address that gap. Based on that, you can have your central hypothesis, like what are the best ways to attain those objectives? And then you have to have some specific aims or tasks, because you have to test your hypothesis if your hypothesis is correct or incorrect, right? Once that's done, you are going to have some scientific outcomes or from some educational outcomes, which is going to go back and make you attain those objectives with the final goal of plugging that gap that you identified in the beginning. So always try to think about these kind of linear logic. And as Dr. Poshke once said, and I pretty much liked it, you need to put your objective as the first line of your first paragraph of your first page, because we are not after a mystery novel where we want to find, okay, what is the objective at the 14th page, right? So you have to put that up front. So these are very important things, and you're going to hear more about this. Based on these things I just showed you, every successful proposal has some element of this logic. And I'm just going to go through a few examples. So these are 3 career proposals that are funded, and we'll use our facility. The first one is by Dr. Alice Alipur from Iowa State University. And she's going to look at infrastructure. Remember, I talked about one of the vision is to look at infrastructure performance. So she's going to look at electrical power infrastructure, and the goal is to harden them. And on the other hand, for the broader impact, she wants to also recruit and retain women and underrepresented minority students in this field and develop university industry partnerships. And together, that's going to work towards hardening the electrical power infrastructure. I talked about CFD and how to reduce physical testing. And this is another career proposal by Professor Catherine Gourlay from Stanford. And she's trying to do advances in CFD for urban flows on wind loading. And she's going to perform experiments at our facility so that we can have more resilient and smart cities, and we can also have energy optimization around the world. So that's her career project. And the last one, which is kind of based on the translation of research into mitigation or innovation, is this one by Victor Maldonado from Texas Tech University. And he is trying to use the knowledge to characterize secondary vortex. You can see a picture of the tip vortices on the right. How can you break down those vortices using secondary vortices? And that's what is going to increase the efficiency of these devices, whether it's a wind turbine or it's a rotorcraft rotor or a gas turbine or whatever. So you can see like that elements, the main elements of NSF proposals are all ingrained in these proposals. We invite you to join our virtual workshop, which we are doing this time with the SIM Center, because we want to do a collaborative workshop where we can show you how the EF tools and the SIM Center numerical tools can be integrated to achieve something which is scientific. So this workshop is going to be on 30th and 31st of July. So unfortunately, the picture you show where we have all the participants in front of the wall of wind due to COVID, that cannot happen. So we have to shift to our online method, unfortunately. But at some point of time, I hope you can come and see these big yellow fans. We are also working not only with the SIM Center, but also with other cross awardees like Lehigh. We are developing a real-time hybrid simulation for wind engineering applications. So we are using Lehigh's expertise in hybrid simulation, and we are tying in our large-scale testing capabilities so we can build large structures and test it separately as a substructure in the wind tunnel, and the whole numerical model can reside in the Lehigh facility. So this is an example of the cross awardee. And the takeaways that Karina wanted us to show, what are the services that we provide? So we provided the users with test specimen design, construction, instrumentation, test protocol and software implementation, operating the wall of wind, of course, getting high video recording and archiving the data, and of course, train users on safety, and also assist users for NSF proposal development stage. If you want to know what are the experimental capabilities we have, what you are thinking, is it feasible? We are there to help you in the proposal development stage. My information is here with my email and my and our website. And then there is an image of how we go through our services. So we start with the proposal development. Then we go with the planning, we go with the training, we help the user for test preparation, execution, and if needed, we help them in analysis and reporting, and then we come up with the project closure and deliverables. With that, I would like to thank the National Science Foundation based on their grant. The grant number is there, and also the Nihiri Natural Hazard Research Community. We are very thankful to this whole network, and we hope that you will become a part of that network, and we can build a resilient community by working together. Thank you.
My screen. So I'm very excited today to talk to you about our wind engineering research facility at the University of Florida. Before I get into the meat of the presentation, since we've just seen the capabilities at FIU, one of the questions that comes up is, what are the differences between the wall of wind at FIU and our boundary layer wind tunnel at the University of Florida? So I'm happy to say we have complementary, but mostly non-overlapping capabilities, and together they represent unique wind hazard research opportunities. So as you've just seen in Arendam's presentation, the wall of wind enables the investigation of large-scale or even full-scale models. This enables the collection of accurate response data. There's going to be minimal scaling errors, and there can be failure mode analysis. The big difference with our facility is that we're looking at scaled models. So the boundary layer wind tunnel investigates load on scaled models under a wide range of wind phenomena. So we can look at complex models and precision control of approach flow conditions. As part of the NHERI network, we certainly welcome projects that utilize both facilities, and we're happy to support you in the development of proposal ideas that would do that. These pictures just kind of highlight the differences. Again, scale being the primary difference between the wall of wind on the right, and you can see a model on the test section of the boundary layer wind tunnel on the left. So our vision for our experimental facility at the University of Florida is to provide users access to a large and diverse suite of wind engineering experimental research infrastructure. Our goal is to support transformative research, and we do this through our state-of-the-art resources, our access to high-performance computing, both co-located with our facility and also design safe. We have fantastic skilled staff and a culture of safety and collegiality that we extend to our users. Our site is located at Powell Laboratory on the East Campus of the University of Florida, and we certainly welcome you to our site. So I'd like to go over the organizational chart of our facility. So Forrest Masters is the PI and the director of the facility. You're going to hear from him later today on the awardee panel. We have collectively a lot of experience securing NSF funding, including 4 career awardees. And so our goal is to really be able to help you with the development of your proposals. Forrest, Kurt Gurley, and Dave Pravat have a long history of collecting field data during hurricane and storm events. Our most recent addition to the team is Brian Phillips. He was actually a user of our facility, and he liked it so much, and we liked him so much that he came and joined our team. And one thing I want to highlight about Brian is he's really pioneered cyber-physical testing in the wind tunnel, which I'll touch on a little bit later in the presentation. He comes from a seismic engineering background, and so that kind of highlights that we want to open up the world of wind hazard engineering to researchers that may not have experience, and we're here to help you along the way to design a proposal and experimental plan, even if you're not familiar with wind engineering. So that brings us to our NSF-funded experimental facility and the resources that we have to offer. So we have 5 experimental resources, 5 of which are based on this idea of pressure loading actuators. So the pressure loading actuators can load full-scale and full-scale wall and cladding systems out of plane with pressure, so they can replay pressures that might be experienced during a storm event or that we might measure in the wind tunnel. In the interest of time, I'm not going to go through the specifics of these pieces of equipment, but I do hope that you go to our website. We've got videos and demonstrations that show how to use the pressure loading actuator equipment. I am, however, going to focus the talk today on our boundary layer wind tunnel. We found that of our 5 experimental resources, this is the one that users have had success in securing NSF funding to use. And I want to highlight how it operates and some of the new technologies we have to offer. So the boundary layer wind tunnel is a 120-foot long open circuit wind tunnel. The reason we want to do wind tunnel testing is we can simulate the boundary layer flows to enable the characterization of wind loading and structural behavior. This gives us a better understanding of wind hazards and improves the way we design these structures. As Arina mentioned, we do rely on computational modeling, but right now computational tools don't have the ability to fully capture some of the complex behaviors that arise with different structural forms and different approach flow configurations. So wind tunnel testing allows us to capture those complex behaviors. Our wind tunnel can accommodate both rigid models, aeroelastic models, and I'll show in just a moment also mechatronic or moving models. So there's nothing non-traditional about the basic operation of our wind tunnel. We have, as I said, it's an open circuit wind tunnel. The wind is generated by 8 vane axial fans at the intake of the wind tunnel. The goal of a boundary layer wind tunnel is just that, to create a boundary layer so that when it reaches the building model, it's a realistic flow condition that the building may see in the real world. So to create the boundary layer, we rely on the development section with roughness elements that are configured in such a way to create the desired boundary layer. And then again, the model would be on the turntable, which is an automated turntable that can model different approach flows on the building model. What is unique about our facility is that in traditional wind tunnel testing, the roughness elements would typically be placed by hand. These would be blocks that you would place to create the boundary layer that you want. However, our facility has the Terraformer. This was funded by an MRI grant. And this is a computer-controlled terrain generator with over 1,100 separate individual elements that are controlled by integrated stepper motors. And if this video plays, you'll be able to see them in operation. The roughness elements can be configured from flush with the floor up to a full height of 16 centimeters. It can be oriented with the narrow edge facing windward and the wide edge facing windward. And the key here is that you can dial up in just a matter of minutes any terrain that you'd like to test for your model experiment. And this really enables us to do high throughput testing because we aren't relying on hand-placed roughness elements. And so, you know, again, in traditional wind tunnel testing, you may only have a handful of terrains that you can configure, and it's time consuming to configure them. Whereas in our facility, we're offering a continuum of terrain conditions. And so by taking advantage of the different orientations of the roughness elements and their heights from 0 to 16 centimeters, we can achieve turbulence intensities from 6 to 40%. And this really, again, offers high throughput testing to investigate phenomena that we haven't seen with more discrete terrains. So the way that we measure the loads on the structures is through the scanning valve system. This gives us 512 pressure channels sampling up to 625 hertz, so we can characterize the loads on the structures in the wind tunnel. And so to give an example of how the Terraformer and the scanning valve would work together, this is a 1/20th scale building model that's instrumented with lines of pressure taps along the roof line. And in this particular study, 33 different terrain conditions were investigated. 33. So, you know, instead of 1, 2, 3, maybe a handful, we can do 33 terrain conditions in just a matter of days. And what this study highlighted is that some of the pressure measurements that were taken really show sensitivity to small changes in the approach flow turbulence. And so being able to have this resolution in the terrains that we can achieve really opened up some new discoveries. Okay, so in addition to measuring the loads on the structure, we also want to be able to measure the flow in the wind tunnel and around the model. So we use Cobra Probes these are kind of multi-hole velocity probes that can measure 3 dimensions of velocity in the wind tunnel. And they're mounted on an automated gantry system. So the gantry system can move these probes throughout the wind tunnel, and these can be done in a preset path, so we can have very precise control of the locations of these measurements. And I just want to kind of highlight one of the projects that took advantage of the precise control and the automated gantry system for flow measurements is a project that was looking at topographic models of Puerto Rico. In the wake of Hurricane Maria, there was interest in investigating the phenomenon of speed up in the mountainous terrains and mountainous regions of Puerto Rico. And so this is a 1 to 3,100 scale topographic model of Puerto Rico. And I will say this was something we fabricated in-house on a 3D router that we have. And again, the Cobra probes were used for very precision measurements of surface flows to investigate that phenomenon. I'll also say that these models are being reused for an NSF Eager project that's incorporating machine learning to predict the speed up in the mountainous regions, and also being leveraged for a NIST project that's also looking at various modeling techniques, incorporating the data from this study. We can also measure flow. Arindam showed their PIV system. We also have a PIV system at the University of Florida. This allows us to have 3D visualization of flow in around the model. And this works by seeding the flow around the model, and then the laser projects the light on the particles, and then we have 2 cameras that track the motion of those particles to give us that 3-dimensional velocity measurement. And it's also mounted on a gantry for precision control of the location of these measurements. This is another view of the PIV system on the gantry. And in the bottom right, you'll see a picture of the PIV operating on again, another topographic model of a section of Puerto Rico there. So now I want to move on to one of the newest additions to our facility, and that is the flow field modulator. This is an active flow control system that enables the modeling of non-neutral and non-stationary flows that are characteristics of some of the damaging kind of thunderstorms, downbursts that Arindam mentioned in his presentation. The flow field modulator, it's made up of 319 ducted fan assemblies that can be individually controlled to achieve the non-stationary flow conditions and non-neutral boundary layers. And this is done by varying the fan speeds on different rows to achieve to achieve these velocity profiles and desired turbulences. So the flow field modulator actually slides in and out of the tunnel. So it slides into the tunnel for the active control flow, or it can be slid out of the tunnel for just standard conventional wind tunnel operation. So this is an optional feature of our facility, and you can see a picture of it here. Now, why the FFM opens up so many new experimental opportunities is we can essentially replay non-stationary data that's been measured in the field. So I mentioned that Forrest and Kurt and Dave Pravat have, again, a history of collecting field data. And what we see in real wind events, real storm events, is that the data is not steady state, it's not stationary. And so to be able to investigate how these types of flows impact structures, it's really critical that we can be able to replay these in the wind tunnel for these types of studies. So in addition to being able to simulate non-stationary squall lines, gust fronts, for example, we can also do non-neutral flows that might be representative of, again, a downburst or a thunderstorm event. So this really opens up new opportunities in wind tunnel testing, and we're actually going to have a virtual user workshop highlighting the flow field modulators. So look out for that announcement. We don't quite have a date set for that, and it will be a virtual workshop. This just shows that non-neutral gust front in the FFM. So I also want to highlight some additional opportunities in wind engineering through cyber-physical testing. So again, our facility has the ability to automate processes, and this really lends itself to cyber-physical testing. So we can loop over test angles with the turntable, we can loop over terrain conditions, we can process data on the fly using the High Performance Computing Center co-located with our facility, or using design-safe resources. Brenham talked about hybrid simulation in the wind tunnel. In their facility, we also offer hybrid simulation studies in our wind tunnel, again, where you have a model in the wind tunnel where you can accurately capture the loads on the structure, and then you have a numerical model that works in unison to study various aerodynamic phenomena. So the other type of cyber-physical testing that we've seen is optimal design of structures using cyber-physical testing. And so the idea with these types of projects, and this study was done by Brian Phillips and Forrest Masters, is really looking at, again, having a model in the wind tunnel that has the ability to be adjusted on the fly. So it might be mechatronic, or it might have moving parts. And the idea is that we run the wind tunnel tests and we optimize the structure in real time. So it couples the results of the wind tunnel tests with a numerical model and an optimization algorithm to achieve the optimal design while the structure is in the wind tunnel. And again, this relies on mechatronic models that can move and be changed in time. So this is a specific example from this project. This is a 1 to 200 scale multi-degree of freedom aeroelastic model. And it has the ability to adjust the stiffness on the fly using 8 adjustable leaf springs. So the stiffness can be tuned to achieve the optimal performance of the structure while satisfying constraints such as displacement limits for occupant comfort. It also has 12 controllable fins, this active fin system, and the position of the fins can be optimized, again, in real time in the wind tunnel, again, to achieve the target design while satisfying the constraints. This is one example of cyber-physical testing in the wind tunnel. So if you come and work with us at our facility, and we hope you do, I want to provide you kind of a flow of how it might look. And so I can't emphasize enough that we are here to help you with your proposal ideas. You'll be assigned a liaison, one of the PIs, to work with you on your proposal, on developing your test ideas, and then we'll work with you on feasibility assessment, developing your test matrix before you submit your proposal to NSF. Once your proposal is funded, we'll work with you to revise the test plan to really refine how the testing is going to go once you come to our facility so you can make the most out of your time with us. And of course, scheduling is done through the NCO. On site, we are here to help you with setting up your tests, running your tests. One thing I want to say is we have a system in place that automatically uploads your data to Design Safe without you having to do anything. So that's kind of automatic running in the background. Once you're done, we're here to help you through the process of publishing your data on Design Safe and publishing your findings. So I think one of the questions asked was, how much does it cost to use these facilities? So what I want to highlight is your NSF-funded researchers, their testing is subsidized. So if you're doing what we call standard testing in our facility, it's no cost to you. So you do not have to include it in the budget of your project. However, if you do have very complex or extensive testing, or if you want to build models, we do have the ability to support that, but we would charge our user fees for those services. We have in-house fabrication that we can offer to you. I mentioned the CNC router that can do large routing of foam, wood, plastics, and aluminum. We have 3D printers for model building, and we have a machine shop and skilled staff that can support both the design and fabrication of your models. So how do you learn more? We have our website. We had a lot to cover today, so I didn't get to a lot of what we have to offer. If you go to our website, you can see more there. You can contact one of our team members. Email address is here. As I mentioned, we'll have an upcoming workshop that we definitely welcome you to attend. It will be virtual, so we'll probably be able to open that up to many attendees. And if you're graduating soon or you're a new faculty member, please do reach out to us. We're here to support you as you prepare your proposals. And again, the takeaway slide, we enable you to investigate loads on complex scaled models under a wide range of precision controlled wind phenomena. We enable high throughput experiments and cyber physical testing through the automation tools we have in our facility. And you have our full support from pre-proposal through closeout. So I really do hope that you contact us, and we look forward to working with you.
So at this point, we will open up the chat for any questions for both the Wall of Wind and the experimental facility at the University of Florida. If you'd like, you can unmute. You can also post the question in the chat box. So there is a question. Can Jennifer tell us what the most challenging part of writing a proposal to use their site? Where do people find the most challenge?
Yeah, so as I mentioned, we really want to open up our facility to folks that may not have a background in wind engineering. And so, I think that the challenge can be really the steep learning curve, but we're here to provide, our resources and our experience to users that, again, may not have a background in wind engineering to help get them up to speed. We can also connect you with collaborators. I didn't mention that in the presentation, but we certainly do not need to be your collaborators, but we are familiar with the research community. And if, say, you need somebody that does CFD or modeling, or you need somebody that has expertise in another area, we can help connect you with them. So I really, we want to lower the bar of entry for those that want to get involved in wind engineering research, and so we're here to help with that. I think another thing that can be challenging is, the cyber physical testing involves fairly complex models. These are models that have moving parts and motors and whatnot, and it can be challenging to conceptualize that, but our staff is experienced in it, and we're here to help you with conceptualizing and designing how those models may look. Hopefully that answered the question.
Yes, thank you. So there's another question. Arindam and Jennifer, can graduate students use your facilities?
Who wants to jump in first? I can say that as part of NSF-funded research, if you're a graduate student researcher on a project, that would be the mechanism for having graduate students use our facility.
And I completely agree, and that's the same in our facility as well.
So Lori was asking because she says she has several graduate students and was wondering if they can apply. There's another question at the Wall of Wind. Can you provide more details about the hybrid simulation setup? Alana was wondering about the typical time scale for projects at these facilities.
Yes, the time scale that we have here, I am not sure exactly, but it's much, so as an example, our time scale could be as low as 1 to 4 rather than, let's say, 1 to 25 or something when we do a reduced scale model testing. And that was one of the advantage that we discussed with Lehigh, that because of the time scale, which is very not much different from the full scale time, when you use actuators or other things, it becomes very valuable, because you don't have to use a very high frequency kind of actuators, which costs a lot. And you don't also have a lot of time for the numerical integration and other things. So that time is an advantage because of the lower time scale that we have. And as an example, what we are trying to do now, we are trying to put a tall building on the top of which we have an communication tower. As you have seen in many structures, they have a communication tower on top of the building for telecommunication, for TVs and things like that. And they are flexible. So what we are doing, we are building an aeroelastic large scale model of that communication tower atop the building. And the entire structure is numerically simulated at Lehigh, including the building and the tower. And the data of the displacement of the tower and its interaction with the building is coming from the wall of wind. And that's where the real-time hybrid simulation kicks in. So we are capturing what is the joint effect of the building and the tower, which is very difficult to just do it in a wind tunnel using small scale models. Even we cannot do it because the building is so large. So that's an example of the hybrid testing that we are doing. We also like to just mention that we have a MEX organization from Purdue led by Dr. Shirley Dyke, and that's also NSF funded, and we are part of that RCN team. And our colleague Dr. Amal El-Awadi from FIU is chairing a committee on hybrid simulation, real-time hybrid simulation, which not only has the FIU project, but all the other different activities going on around US and in the world. So highly encourage you to look at MEX and RCN so you can get more details of where real-time hybrid simulation is going in this.
Thank you, Arinda. And we have one last question for both Dr. Bridge and Dr. Chowdhury. Do you see a growing trend of hybrid simulation use in wind engineering and other natural hazards in general?
Can you repeat that question again, Karina, please?
Yes. So do you see a growing trend of hybrid simulation use in wind engineering, as well as other natural hazards?
Yes, yes. And the two examples is the new committee that has been formed on under the direction of Purdue, which is the RCN program under the MEX. And you will be amazed to see how many applications there are being discussed. Like Jennifer mentioned one at their facility, we have one, and there's so many in various parts of the US on hybrid simulation. And to add to that, a recent project has been funded by NSF. The PIs are Dr. Teng Wu and Dr. Wei Song, and they are going to do a real-time hybrid simulation at our facility. So this will be the first NSF project that will use real-time hybrid simulation in your facility by Teng Wu and Wei Song. So there are many examples which corroborates this thing about hybrid simulation getting into other natural hazards.
Okay, thank you both thank you all for your questions, and thank you, Dr. Bridge and Dr. Chowdhury, for answering those questions. While we set up for the next one, we did have one other one just on how grad students are trained to use the facilities. So if you can take a quick minute to answer that question, that would be great.
Yeah, so when users come into our facility, so our staff operates the equipment, but our grad students are there the whole time the tests, graduate students that come in to use the facility are there the whole time the tests are being run. So we don't actually have our users operate our equipment, but we certainly want to train them on the principles of the experiments, the data collection, and the analysis, and they do that by working with our staff and our PIs and our graduate students that are on site.
Okay, now first of all, I want to welcome everyone. I don't know how many people are on. It looks like there's 44, but I want to welcome everyone here to the virtual Summer Institute. These are trying times, but we'll get through it. And thank you, Karina, for the opportunity to present the Lehigh Summer Institute. This is going to be a little bit quick because we don't have a lot of time. Normally we have more time than what we have, but with these trying times, we'll do the best we can. So what I'll talk about, I'll give you an overview of the facility at Lehigh called the Niri Lehigh EF Experimental Facility, discuss briefly some experimental protocols, talk about the infrastructure, and then show you just one or two of the selected research projects, and then conclude with some preparation resources for your proposals. The overall idea is to provide you information and stir your interest and curiosity for using not only our site, but some of the other facilities as well within the within the Niri community. So what is the Niri Lehigh Experimental Facility? Well, we're basically a multi-directional, but we can also do real-time natural hazard simulation facility. We're unique in terms of the portfolio of equipment. Sorry, equipment, instrumentation, infrastructure, test beds, and also the control protocols we use for experimentation. We can do large-scale multi-experiments by the size of our facility in the lower right side. You see that we have an experienced staff, some have been there for a very long time. And as I mentioned, multi-direction, large-scale. This includes real-time hybrid simulations. It's not the only thing we do, but something we do. We've been doing for the last 20 years, and this allows you to combine experimental and numerical simulations. And I'll show some of these examples in a minute. What I want to also emphasize is that we exist within the Atlas Center, which was the original NSF Center established in 1987. That provides us with a huge array of additional resources for the research that want to use our facility. This is our, sorry, I got to move something here. This is our organizational structure. I'm the PI. The co-PI is Richard Souse. Chad Kusko, you may have heard talking, is our ops manager. Leon Cal, who's also online, is a research engineer. We also then have Tommy Morella, who's our IT systems manager, has a very strong background in computer science and also hardware, quite handy person. And then we're supported also by some Atlas personnel. We hire them as on need basis, such as a lab manager, IT support, and financial management. Now, we always look to progress forward. So we have capacity building partners, particularly Professor Shamin Paksad and Professor Mohammed Suleiman, who are building capacity and structure monitoring advanced sensors and soil structure interaction. Our uniqueness is large capacity, equipment and facilities. So you see some examples here of the large capacity dynamic actuators. They're the ones colored in blue. We have advanced instrumentation. The lower left shows the reaction wall and strong floor. That was taken in 1987. It's never been empty since for the reason that we're quite active. We have real-time computational modeling. The control room is in the middle lower bottom of the slide, and large-scale test beds. The actuators that we have are kind of like the heart of our facility. They're reconfigurable. Like you see the capacity and the number of those actuators, the stroke, and the maximum velocity. They're very dynamically oriented. The advanced instrumentation includes DIC, digital image correlation. This is basically non-contact type instrumentation, very handy. And we actually have 3 of these systems, actually 4, excuse me, and the measurement range and resolution is shown. Our real-time computational modeling is centered around a real-time integrated control system, which has ScramNet, basically shared memory. In that, we've put algorithms, including explicit integration schemes that we developed from the ground up. We have adaptive, multi-directional servo-hydraulic actuator control in order to make sure that the tests that the users are undertaking are done accurately. And also, we've been expanding this to where now we're also doing real-time online model updating. The test beds, I'll go into more detail in a minute here, but basically allows you to make use of the large reaction wall and the strong floor. These test beds already exist at Lehigh. You can test structural components, structural systems, or non-structural systems, the details of which I'll lay out in a second here. before I get to, let me talk about the experimental protocols. And first, maybe I should describe hybrid simulation. I'll put the word in real time and then describe what the difference between that is, what you heard maybe before, dynamic substructure or pseudodynamic testing or hybrid simulation. Let's take an example project that Professor Simon LaFleur from Iowa State was a PI on. And they're looking to place semi-active devices such as dampers between cladding of a structure or building, which all buildings have it, and the structural system. And that's to alleviate some of the effects of natural hazards such as wind or earthquake. So if you take the example from wind, or interested in knowing how this system performs in these devices, how effective they may be, wind tunnel testing is done here to get the pressure distribution from which the wind tunnel loads can be obtained. And the example here could be University of Florida or FIU. We've actually used both facilities, and the researchers have. Having that wind pressure distribution and history, the structure is divided into an experimental analytical substructure, right and left. The reason being is because you can't put the whole system in the lab. Perhaps you can also not model the dampers if they're new devices. So in order to get the most accurate answer, you divide these in these two subdomains. There's a simulation coordinator that integrates the equations of motion at each time step, and this point in time is I+1. With the forcing function predefined, or it could evolve during the course of testing based on the display shape of the structure, you'll integrate the equations of motion, or the system will integrate the equations of motion and generate command displacements, which will be sent to the two substructures, from which restoring forces will come back. The left side is computed, the right side of this slide is measured. And this is repeated for each time step moving forward in time. And at the end of that, you'll have the real-time structural response if it's done in real time. If you slow the system down, not the integration process, but the application of load in the experimental substructure, then it'd be called what's an expanded time scale. So why would you want to do hybrid simulation? It's basically very cost effective. You can account for the complete system and the interaction of the component that you're looking at and interested in, yet you may not be able to numerically model that. The goal there is to try to look at the interaction of that component with the rest of the system and their realistic loading, which you could also impose. In real time, the method accounts for rate dependency, which a lot of rate dependent devices are evolving or have been used in order to mitigate the effects of natural hazards. And so that's very important. Now, I've talked about hybrid simulation. This is an example, large scale hybrid simulation. We also could slow it down, as I mentioned. These are some example projects ongoing or in the past in the lab. You can do the whole system except for maybe the mass or other aspects, but you could also just put the devices in the test beds or the laboratory. You could also do geographic. So if your laboratory has a device that you want to keep in your lab, or there's something special about that, it's possible to do the hybrid simulation via the use of the internet. We've done that a number of times, and also actually done that in real time. This particular project here was won by Richard Christensen, and at that time a student, Mr. Kim or Dr. Kim from UConn. Now, a lot of you may not be interested in hybrid simulation. That's well understood. We do a lot of other types of simulation or testing, should I say, such as using predefined load or displacements just to characterize quasi-statically or dynamically devices such as dampers. Here they're shown a damper in the upper part of the slide. The lower right shows a temperature chamber, which we're looking at that time. The researchers themselves were looking at the effects of temperature on the damper characteristics. New generation damper, semi-active rotary friction device is also being characterized as another example. Now they could be small or it could be almost complete systems. Here is basically a coupled shear wall, 3D shear wall that was characterized under combined axial and lateral load. And also dynamic testing. So in those prior tests, it was slowed down. If you speed things up, that's predefined dynamic testing. It's a three-dimensional piping system here is subjected to earthquake loading. Now, some of the infrastructure, test beds, let me begin with that. This is a lateral load resisting frame test bed. The rust-colored bracing frame is not the structure here. This is actually the test bed. It stabilizes what would be a lateral load resisting system in the plane of that system within what we call the bird cage, or the bracing frame here. The dimensions are shown in the part of the slide there. You can use this to perform characterization or real-time hybrid simulations or slow down, whatever you fuels necessary for your work. We also have non-structural, multi-directional dynamic loading simulator. It enables you to do multi-directional hybrid simulation or just non-structural component characterization. The dimensions are shown there. And I talked about, you saw the picture with the actuators. This is actually the full-scale damper test beds. Again, for characterization or hybrid simulations. The capacities are really just based on the actuator. And you see the capacities there, maximum stroke, velocities, and forces. These are, the actuators are in blue and the dampers are identified that are next to them. We also have a real-time cyber physical structural systems laboratory. It's sort of our latest entity that we've added to our facility to try to keep growing and provide resources to the users. This is used for research as well as ECO and training. Has 5 actuators, MTS actuators. The model numbers are there. It may not mean much to you, but below you see the specifications. These actuators range in capacity from 50 to 100 kilonewtons. The velocity is as large as 1.3 meters per second. Photographs in the upper right hand shows the 5 actuators with test beds, and within those test beds we have readily available, if the researchers want to use them, are 4 nonlinear viscous dampers and also a rotary friction damper, which is will be made semi-active. Storm surge, is very important. Storm surge debris, could be generated impact harbor and coastal facilities. So we have a tsunami and storm surge debris impact force test bed. Also, we have some soil boxes. They're not large. They're what we call reduced scale, but not necessarily that small. They're also within the facility. The dimensions are shown here, and it includes advanced sensors for measuring response of the soil and the foundation that may be embedded in the soil. The integrated control system actually is what, as the name implies, controls things in real time. There's something that Tom and real IT person put together here. What it allows you to do is configure the experimental protocol as a user. We provide this service in order to perform your test. And so the various methods I talked about are shown there. There's even ones that be added to this if you wish, something that may evolve that you're interested in. The algorithms reside on what's called the XPC. This is a real-time Red Hat operating system. And I mentioned a few times it could be run either in real time or what we call an expanded timescale, where we slow down the application load of the actuators if real time is not required. It's a very flexible system. We can do distributed hybrid simulation using OpenFresco, which is used in conjunction with perhaps OpenSeas or other software, but we've also have customized software that we've written or others have written that we've incorporated into the system used for that purpose. And it's a very flexible design. I just mentioned the fact that, we can have software and middleware packages developed by people such as yourself or the NHERI CI that could be plugged in and utilized. Now, hybrid simulation, we've evolved over the last, I should say, almost 30 years. I had a keen interest in this ever since I was a student. And we've now evolved where we use explicit schemes, so they're unconditionally stable. They're dissipative, which is very important. I'm referencing some algorithms here. I'll give you reference to these citations. If you don't write this down, it's okay. Don't worry, I'll tell you where you can find these. But we work in an explicit domain and also have adaptive actuator controls such that the effects of latency and error in actuator motion is alleviated. And this is very important because actuator control, if it's not handled properly, the test literally will become chaotic. So we've developed these schemes, and they're very user-friendly, and they're quite accurate to the extent that MTS themselves have actually incorporated this into their own controllers. Now, the hybrid simulation, if you're concerned about using whatever software, we've written our customized software, which is based on theory that some of which doesn't even exist in OpenSeas yet. But if you want to use OpenSeas, we've done that as well with the interface of OpenFresco. So that's just sort of illustrated here. Particular software I'm talking about is Hybrid FEM. It has numerous conditions for boundary conditions, constraints, or restraints, assortment of elements, including some fiber-based elements which are explicit-based. They don't exist in OpenSeas. What these algorithms allow you to do is actually operate in real time. And if you want to, in fact, use this for just numerical simulation, we benchmark it and it runs 2,000 times faster than OpenSeas, because OpenSeas, if it's implicit, it's a very good program, OpenSeas, but if you run things in explicit form, it's much faster because of the convergence approach there. We also have real-time online model updating, assortment of other things here. We can model concrete, steel, any materials for which you define the stress strain curve. The materials include what I show on the right. We can also model initial stress, such as allows you to do post-tensioning or pre-stressing. You have tension compression gaps, and also fracture. And the fracture could be wrapped around any of these materials that are listed above there. Now we have a lot of space in our facility. I don't have a floor plan, but it's a quite large facility. The reaction wall itself runs about 100 feet down the side of the lab, and the lab itself is much bigger than that. Within that area, we have large doors at the front, allows you to bring specimens in if they're not going to be made in the lab, but if they are, we have the specimen prep area called the staging area. We have several of these throughout the facility. In the machine shop here, a braced frame with dampers. The damper is not replaced yet, it is being lifted by a crane into position for testing. We have several auxiliary equipment and laboratories that are noted here, including mechanical testing. You could do material testing, it's often important. Visitors have access to a dedicated office as a researcher, your students, or the staff. We have meeting rooms where we hold our workshops, auditorium in particular, and a conference room, storage areas, and the facility is secure. It's locked up at night. Police patrol it every a few times each night, and it's always under constant surveillance there. Some selected projects, one of which here involved Princeton, Purdue, and Lehigh in Taiwan, was self-centering systems. You may have heard of these, something we actually developed at Lehigh back at about 2000 with self-centering mold resisting frames in particular. This was done using hybrid simulation. It wasn't done in real time, expanded time scale, but the video, which Tommy can do this for you, had the data shown here. This is split screen. This is actually played back in real time, in which this particular structure was subjected to the 2,500 year return period. That's called the NCE. And you see various video here, this connection here, shown here. The gap's going to open as post-tension, so it's not a failure. This is the moment rotation relative to the beam and column, and it's self-centering coming back to the origin. The lateral floor displacement of the 4 floors here, and describe the structure very well, but you can see the 4 floors here are placed here. If I were to run this all the way through, this would self-center at the end of the event here. This is a 0 floor displacement. Now dampers, this particular dampers, tailored devices, these are large scale dampers. We had people characterize these, develop models for these. Here are some of the characterization tests. They're rate dependent, as shown here by the hysteresis, which are from characterization tests. Same amplitude, just different frequencies. This is a damper force velocity, so it's not linear, so it's definitely a nonlinear device. So we're well suited to do characterization tests of device, particularly dampers like this, but this was used to do some hybrid simulation. This is an earthquake hybrid simulation. You can see the analytical experimental substructures, video of the dampers themselves. This is the hysteresis, definitely not linear. And the displacement, it's going to come back to 0. So that structure remained elastic. I apologize for the noise, but sort of don't apologize, because if you don't hear the noise, that's actually in real time, you believe it. So that's the purpose of that. This was a mixed mode hybrid simulation, which was mixed mode being displacement and force. It was led by Notre Dame, University of Texas at Tyler, coupled shear walls with interface between the lower physical and the upper part numerically modeled, had advanced instrumentation, including digital image correlation, measure deformations in the shear walls and the coupling beams. Second to last project, we're involved with multi-hazard or not multi-hazard facility. This is looking at tall buildings, semi-active controlled cladding was one of the projects here. There's the universities involved. The floor plan shown in the lower left. The structure in the upper right is a 40-story building with steel frame, with buckling restrained braces and outriggers. Nonlinear viscous dampers were added to the outriggers to try to improve the behavior, particularly under wind loading, a multi-hazard involved earthquake and wind loading. The wind loading itself was obtained from FIU, Florida Institute, Florida International University. The substructures here involved there are 12 dampers connected between the outrigger trusses and the outrigger columns. One was physically in the lab. The remaining 11 were modeled with model updating using the measurements from the one damper that's noted there. To our knowledge, this is the biggest hybrid simulation ever conducted. It's almost 8,000 degrees of freedom and the number of elements which are nonlinear. This is the numerical part of this. It used reduced order modeling, geometric nonlinearities. The mass inherent damping are modeled numerically. Now, the hybrid simulation of model updating, this is the one damper in the position here. The measurements from that are used and passed through at some new elements that have been developed called a nonlinear explicit Maxwell model, but it's for the dampers in which the unscented Kalman filter used to update the model for these dampers, and that was used. Here's video for the earthquake. I'm not going to play it all the way through. It's done in real time. You see here's the BRBs modeled numerically throughout the structure. They're nonlinear. This is the roof displacement in the east, west, north, south direction. This is one of the dampers, and ground accelerations and lateral displacements in the two directions at 4 different levels. Same structure. Yes.
Hey, Jim, this is Joanne Browning. Just wanting to let you know that if you could wrap it up in the next minute or so, that'd be wonderful. We do have another presentation coming.
Yeah, I'll be done. Sorry, just a minute. So under wind loading, you know, we also did wind loading. I won't play it through, but it behaves differently. So we see the wind loading. It makes a difference in terms of the dampers. And Carrie Ryan did non-structural component testing with trying to see if she can improve the behavior of this. This was put under bidirectional loading. It shows some of the test it was placed in the structural system here. And in terms of preparation, we have a workshop. All facilities do. It's worth taking advantage of because information is disseminated there, useful for proposal preparation. Our website's noted here. We have numerous resources describe the facility, the protocols for the equipment, experimental protocols, payload protocols, in addition some projects there that are noted there. And the very last page for resources, you should go to these where you can find some of the things I pointed out, particularly on the references that are noted here. And these are workshops that are archived, and the contact information is here, which again, repeated here, in which Chad Kusko I just placed as a point of contact, but you're welcome to contact any of us, and this is the website. And with that, I want to acknowledge NSF, and thank you very much.
All right, thanks for having me here today. So I'm going to be talking about the NHERI at U-Texas facility, where we have large mobile shakers for natural hazards engineering field studies. So I'm going to give a little overview of our facility, the resources, and highlight some projects to show off some of those capabilities. So first of all, the team. It's led, the PI is Ken Stokey of UT Austin, and the co-PIs are myself from UT Austin and Brady Cox, who's at UT Austin but will soon be transferring over to Utah State University. We have a number of technicians and operations manager. So I'll point out Dr. Barnyu Mung. He is our operations manager. He's going to be your point of contact for questions about setting up proposals and that sort of thing. And I'll have his contact information at the end of this presentation. And then we have several technicians and IT specialists. Looking at our resources. So we have a large number of shaker trucks. That is our major resources. The 3 that you probably may have heard about before, our largest 3, are called T-Rex. It can shake in 3 directions, triaxial shaker. Liquidator, which has capabilities of going to very low frequencies. And Thumper, which is what we call our urban shaker. It's a smaller shaker that's street legal, can get a little tighter, closer into buildings. And those are the 3 primarily used shakers. We also have other shakers, Raptor and Rattler, which I'll show a little example of. They can be paired with some of our other shakers to help increase the soil strains that we can generate in the field. We also, because we are a field testing site, we have a number of support vehicles, so a big rig to transport those large trucks that are not street legal, to transport them to sites, field support truck for fuel out in the field, an instrumentation van and trailer with air conditioning, which, believe me, you really want when you're out in the field, in particular locations in the summer. And that's where we keep all of our data acquisition systems and sensors. And then we also have capabilities on some of our trucks. For example, hydraulic cylinders to push in sensors down into the ground. So if you want more details about each of these shakers, including the force versus frequency output of these shakers, that's all available through the documentation on our DesignSafe website. In terms of instrumentations, we have a wide array of instrumentations, geophones, lots of geophones. For those structural engineers like I am, I just refer to geophones as velocity sensors. That's really what they are. But they're commonly used in geotechnical practice, but can also be used to monitor vibrations in structures as well. Broadband seismometers, triaxial accelerometers, load cells, CPT equipment, and so on. And we can also produce pore water pressure, customized pore water pressure sensors that can be embedded into the ground as well. So a large array, data acquisition capable of supporting all of these sensors, including with also the capabilities that you can bring your own sensors and plug them into our data acquisition system. I should note too that because a lot of our research is in the field, you might have geographically distributed field that you're looking at. So we can accommodate both wired sensors as well as through these Taurus digitizers, they can be they're GPS based, so they can be isolated at different locations and essentially deliver the data back wirelessly. So our motto is that we have shaker trucks and will travel. Unlike the other facilities that are facilities located at one location, a lab that you would go to and test, instead we are a mobile facility. So we go into the field to test in the field. So this is testing infrastructure that might be very difficult to replicate in a laboratory setting. So examples of places that these mobile shakers have been over the past, I don't know, that we're nearing 20 years now, as part of NICE and now part of NHERI. So they've been to, as far as New Zealand, the shaker trucks have been, Hawaii, and in really the four corners of the United States. Well, I think we need to find a project in Alaska to really hit, and maybe in Puerto Rico as well, to really hit all the four corners. So we can go wherever the system that you are interested in investigating, we can go there. So I want to highlight our projects based on our science plan and our science vision. So our science plan consists of 3 parts. The first part is to improve subsurface imaging and in-situ anomaly detection of both 2D and 3-dimensional fields. So an example of this might be trying to image a levee. That is some of our aging infrastructure we have in this country. And to be able to assess the condition of that levee, to identify anomalies so that those can be better repaired, will help improve resilience of our communities. For each of these aspects of our science plan, we have housed or hosted different workshops associated with each of those science plan initiatives. So if you go to our DesignSafe website, you'll find all the presentations and data from those workshops so that you can see what exactly was done. Another example of subsurface imaging was some testing to look at sinkhole identification and imaging. And I'll show a little example of that later. The next aspect of our science plan is in-situ liquefaction and nonlinear soil testing. So this is using the trucks to generate large strains, monitoring pore water pressure to look at different liquefaction mitigation techniques in different types of soils. And we hosted a workshop in 2016 looking at Willamette soils near Portland, Oregon. And again, I'll talk a little bit more about that project here in a bit. And then our final aspect of our science plan is using the trucks for structural health monitoring and soil foundation structure interaction studies. These trucks, they're just dynamic excitation. So they can be attached to or driven on top of structures or shaken around structures to excite them dynamically. And I'll also talk about a project and a workshop that we hosted in New Jersey where we did this sort of testing on a bridge to look at soil foundation structure interaction studies. So for each of these, I'm gonna talk a little bit more about specific projects related to each science plan. So the first aspect of our science plan, the performing deeper, more accurate, high resolution 2D and 3D subsurface geotechnical imaging. So thinking about the motivation of this, you look back at ultrasounds that were used in medical professions. And they were always these kind of grainy, two-dimensional, like I think maybe there's a baby in there, I'm not sure. But you look at what we've been able to do today, and through these, through new ultrasound techniques, you're able to really get a 3D image of a baby, right? So why not be able to do that with our ground, our soil? Historically, we have been able to create one-dimensional shear wave velocity profiles that gives you information about the stiffness and the profile of soil in a column at a specific site. But really what we need to create more resilient and robust infrastructures to have a better idea of the three-dimensional variation of important engineering parameters like shear wave velocity and P wave velocity. This is very important for site characterization and characterization of different ground motions that a location might experience. So that's what we're shooting for in our research vision. So some project highlights under this topic. So this first project was a project looking at site characterization with 3D seismic waveform tomography. And what this project was doing was trying to characterize both shear wave and P wave velocity or compression wave velocity from subsurface-based seismic wave fields. So what does that mean? So this is using the shaker trucks as seismic input and using an array of geophones as receivers to see what seismic shaking comes back to the surface. And from that, using full waveform inversion to create three-dimensional profiles of shear wave and compression wave velocity at that site. And in this particular site, this was a site in Florida where there was a sinkhole. And there was an SPT, standard penetration test that was done at one location. You can see the results over here where you can see at one location a void was detected because there was no resistance. So there we knew there was a void at that one location. But to characterize the three-dimensional aspects of that anomaly or that sinkhole would be very difficult. You're going to have to poke the ground everywhere, and that's just not practical. So using these techniques with the shaker trucks, you can generate that 3D profile of the anomaly and find those voids without just the luck of the draw of did you poke in the right location to find those sinkholes and those voids. And here's an example of the capabilities that we have that facilitate this type of research, is that to do this type of research, you need a large array of sensors. In this case, we use 4.5 hertz geophones, kind of meshed out on the surface. And you need to be able to shake or provide that excitation at many different locations. And because our shakers are on wheels, they can be moved pretty rapidly and shake at multiple locations. And that's important to be able to generate these subsurface 3D images. The next aspect of our science plan is characterizing nonlinear dynamic response and liquefaction resistance for complex geomaterials in situ. And in situ is important here because there are some complex materials that are very difficult to sample from the field and bring back to the laboratory without changing their inherent characteristics. So an example of this, a project was looking at the cyclic response of transitional soils. And this was the project of the Willamette soils near Portland, Oregon. So these are typically difficult materials to characterize. So in this project, what we did also was improved our procedures by taking 2 trucks side by side, syncing them together, shaking them simultaneously so that they were able to generate much larger shear strains in the ground beneath, so that we were able to get much further, much closer to that excess pore water pressure that generates liquefaction. So we more than doubled the shear strains subsurface based on this new technique that we were able to develop as part of this project. Another example of this is looking at microbial induced desaturation techniques to mitigate liquefaction. So here's an example of tests. These tests have been done in Toronto as well, in the Portland site, to look at these microbial induced desaturation techniques. And with our testing capabilities to look at compression wave velocity profiles beneath the soil, you're able to see that once with those biological improvements, that you actually were able to desaturate the soil and provide a much higher resistance to liquefaction. And again, that needs to be done in the field to actually show that this can work at larger scales in the real world. The last aspect of our science plan is rapid in-situ methods for non-destructive structural evaluation and soil structure foundation interaction studies. So here, looking at different test methods that you can use with the shaker trucks. So as I mentioned before, you can drive the shaker trucks onto a structure. That works particularly well for bridges or parking garages, but you can also remove the shakers from the truck and mount them directly onto the structure if it's a structure that you cannot drive on, for example. You can also shake the ground around the structure to induce those vibrations. And another option that's less commonly used, but I want to highlight that it is an option, is that these trucks, they use hydraulics to power the shakers. Those hydraulics could equally be used to power something else. Maybe you have a hydraulic actuator that you want to take out into the field to do more quasi-static type loading. And you can do that using these hydraulics on this truck as a platform. We also have winches on the trucks that you could use to do like a pullover test in the field as well. Project highlight here, this was some testing done on a bridge in New Jersey, looking at using the trucks to generate large amplitude force vibration tests and really studying the soil foundation structure interactions and what benefits you get from this large amplitude force vibration as compared to ambient vibrations that are commonly used. So here we had an array of sensors on the bridge deck, on the bridge bents, and on the ground around the bridge, and we were able to drive our shaker T-Rex onto the bridge and shake at many locations and in many directions on the bridge. The main motivation for this project is that much of the conventional structural identification that uses ambient or low level shaking really is not able to exceed some of those stick slip mechanisms that are inherent in most structures, and they aren't able to really engage that soil foundation structure interaction. So if you really are trying to look at the response closer to the safety limit, you want to have force vibrations that exceed those stick slip mechanisms and are able to actually look at the nonlinearity that you might get from those soil foundation structures and interactions as well. So some results from this test is this is looking at the results from some geophones, again, velocity sensors on the bridge bent due to transverse shaking, and we had ambient shaking as well as shaking at higher force outputs. And this is the velocity versus frequency plot. And what you notice is that peak, the peak at which the peak velocity, the frequency at which that occurs shifts. So this indicates the period shifting due to the increased amplitude. So that structure is softening, if you want to say that, due to the increased shaking amplitude. And this is not because it's going nonlinear in terms of what structural engineers often think of damage to the structure, but it's actually because it's engaging that soil foundation structure interaction that would not have been engaged with just low level shaking or ambient vibrations. And the researchers at Rutgers are validating this and showing this using some finite element analyses that include soil foundation structure interaction and those that do not, and showing that accounting for that soil foundation structure interaction is able to replicate this shift in period that was observed. Last project highlight that I want to mention here is a recent project looking at seismic isolation of embedded structures, underground structures, using periodic metamaterial barriers And here is an example of, have this idea for a periodic material-based seismic isolator, but you want to understand how it actually dampens or attenuates seismic waves in the field. And what we were able to do is, because this particular study was on a new type of isolator, we didn't have to go to some exotic location around the world to study a specific type of soil that we were able to find. We're actually able to do these tests in Austin, which greatly reduced the travel cost and the fuel cost for the trucks because it's local. So that's another, we have an area in Austin where we can do some tests like this if that fits your need for your research project. So here we are embedding these isolators in the ground. We have another example on the right where we have one of these periodic isolators, and we put a little structure on the top. And this is an example of where we take the shaker that is usually mounted on Thumper, but we disconnect it and mount it to this little structure to create vibrations on the structure that might be modeling vibrations caused by wind, to see how those vibrations propagate through the foundation and into the soil, and if that periodic foundation is able to help attenuate some of those vibrations. All right, so that is the quick overview of our resources and some sample projects. What I want to leave you with is that we have these large mobile shakers that can go anywhere. They can test geotechnical and structural systems in situ, and a wide array of sensors that can be used, and data acquisition systems that are used in the field. And if you have questions, the best person to contact, his information is also on our website, but here is his email. Here's our site manager, Dr. Mung.
So my goal here is to, in 15 minutes, give you an overview of the NHERI at UCSD shake table facility, which is currently under upgrade to 6 degrees of freedom with funding from the National Science Foundation and some financial resources from our university. And then talk about new research opportunity that will be made possible by the 6 degree of freedom LH post, which I think will be interesting for the young faculty writing proposal. So let's look at the, what you would see if you were to come to the site. So the shake table is located at the Engelkerk Structural Engineering Center. You see the shake table here in yellow. Here we have some electrical pole and transmission line being tested. There is the hydraulic power building that has the huge hydraulic power that we need to run that facility, even more so now with the 6 degree of freedom. We also have a blast impact facility that is not part of NHERI here, housed in the building. We also have a soil structure interaction facility here. Let me see if I can, with 2 soil pit, natural soil pit 21 feet deep on each side with a large reaction wall that can be used by NHERI researchers, but it's not part of our NHERI site, so it can be used on a recharge basis. You see our laminous soil box in a few pieces here. At the site, what is important to know also is that we have a few years ago built a very large slab that is actually larger than the planned size of the shake table platen. It's a 3 feet deep, heavily reinforced. It has a large array of tie down like the platen of the shake table. The goal is to increase the throughput of the facility. If you have a specimen that weighs less than 100 tons, can be constructed there and then moved by crane on the shake table. Or part of a large structural specimen could be assembled on that slab and then moved to the shake table to speed up the construction. You can see a picture here of that slab. Now, a few words about the NHERI at UCSD San Diego team. So I'm the PI. There are 4 co-PIs, Professor Tara Hutchinson, Gilberto Mosquera, Benson Ching, Lely van den Einde, with their area of expertise indicated here. We have 2 senior personnel, Professor Jose Restrepo and Enrique Luco, who were the first 2 PIs on the site underneath. We have an acting site operation manager, Kurosh Loftizadeh, shake table operator Darren Mackay, Robert Beckley, the IT manager, and two very talented development technician, Alex Sherman and Jeremy Fitcher. Alex Sherman is also the site foreman. So in our science plan, you know, the vision of our site is rooted on three critical needs. We need much more, we need to understand much better the system level behavior of buildings, bridges, critical civil infrastructure system, from the initiation of damage all the way to the onset of collapse. We need data at the system level to support the development, calibration, and validation of high fidelity physics-based computational model that will allow us to rely less in the future on physical testing and more on model-based simulation for seismic design and performance assessment of civil structures. And finally, large-scale shake table tests are the ultimate level of validation of new ideas in terms of new material, component, system, seismic retrofit methods for protecting the civil infrastructure from earthquakes. When we designed our shake table in 2001, 2002, one of the main design objectives was to be able to reproduce very severe earthquake ground motions, especially those produced by near source ground motions. And since we have a mild climate here in San Diego, we decided to build it outdoor. So this is the largest outdoor shake table in the world. We have no height limitation, so we can test, you know, many specimens that are full scale, or if not, they are very large scale. So far, I have counted 34 major research and commercial projects in the period from 2004 to 2019, so 15 years. A lot of building specimen, but also some geostructures, some wind turbine like you see here. So this is probably one of the last time that we will show this slide here, since we're now upgraded. So this is, you know, the 1 degree of freedom LH post is history now. And the 6 degree of freedom is under construction. So even when we conceived and designed this shake table in 2001, we conceived it as a 6 degree of freedom shake table, but built only 1 degree of freedom because of the budget limitation at the time. So here you have the salient, the characteristic features of the 1 degree of freedom LH post. It could move plus or minus 75 centimeters. You see the size, 40 feet by 25 feet. The peak velocity was a major design parameter, 1.8 meter per second, to reproduce the large velocity pulses from near fault earthquakes. In order to reproduce this velocity, you need an incredible flow of oil, 10,000 gallons per minute, peak flow. The maximum horizontal force is 680 ton force. So if we have a 500 ton rigid payload on the platen, we can move it at 1.05 G. We have a maximum payload capacity of 2,000 ton force, which is very, very large, largest in the world. And our frequency bandwidth is 0 to 33 Hertz. And we have a very large overturning moment capacity. So you can see here the table in actions. You can see the little wing here. We have 4 wings like that were kind of forcing it to move perfectly in a 1 degree of freedom, so that they have already been cut off for the 6 degree of freedom upgrade. They will not be there anymore. This slide also very important to give you the level of accuracy at which we can reproduce earthquake record. You have an example here for this specimen where we wanted to reproduce the Canoga Park earthquake record from the 1994 Northridge earthquake. So the target is in accelerogram is in red, the achieved is in blue. You have a zoom here. You see a very, very good level of accuracy for such a large shake tables. Very, very challenging to achieve. You see the spectral acceleration also here, target and achieved, and the spectral displacement target and achieved. All tests that are performed on the LH post, they are densely instrumented. typically hundreds of sensors are deployed on the specimen. So we have 12 data acquisition nodes of 64 channels each, giving us over 700 channels, sampling up to 500 sample per second, and with an AD conversion at 16 bits. It's not official yet, but we think we have found the funding to upgrade the data acquisition as well. That was becoming obsolete. The part could not be replaced. It's from National Instrument. So we very likely will have the same number of channels, but at 24 bits with simultaneous sampling, and a much larger number of, I think, up to 25,000 samples per second per channel. You can see here the type of sensors that we have in our inventory. Accelerometers, displacement transducers, strain potentiometers. Strain gauges are disposable. Load jack, load cells, soil pressure transducers. We have a GPS system that allows us to measure the displacement in 3 directions with an accuracy of about 1.5 millimeter at 50 hertz. We have an array of high-speed camera that are very important that can be synchronized with the sensors. And we have also a fully configured end-to-end live video streaming projection system that Robert Beckley has put together in these last few years. And Robert also has put us on social media with YouTube, Facebook, Twitter. And we have some calibration equipment for the data acquisition system and sensors, because we are also accredited through the international accreditation. So we also have, when we want to test soil foundation structure system or geostructures, we have 2 large soil boxes that you can see here, a laminar soil shear box and a bigger, you can see the dimensions here, we call it a stiff soil confinement box. So it allows us to investigate the seismic response behavior of soil foundation structural system, and together or in synergy with the centrifuge test, help validate computational models. We also can study the effect of soil liquefaction, lateral soil spreading, by putting a bladder in the box before putting the different layers of soil. We also have some basic hardware and software for real-time hybrid shake table testing that are listed here. 2 years ago, Gilberto Mosqueda performed some commissioning hybrid shake table test on a system similar to the first example that I showed here, where the top floors of a building would be used as an inertial damper for the building. It would be connected to the rest of the building through some passive or semi-active devices here. So we would test on the shake table only these top floors with the devices, and the rest of the building would be modeled in the computer. Or in the case of a full building base mat, pile foundation system, we would have the base mat and the pile foundation, the surrounding soil model in the computer, and the building on top of the platen. These are, of course, very, very challenging problem that will require a lot of research. One of the biggest obstacle is safety of the shake table system in debugging the system, so to speak, to run this kind of hybrid experiment. So here you see a picture with a number of specimens that we tested in the past. See a variety of buildings, reinforced concrete, masonry, steel, bridge piers, retaining wall here. So I'm going to, since I have only 15 minutes, I'm going to show only one of them here. You see a 4-story building where the lateral system was partially decoupled from the gravity system. Professor Fleischmann And Richard Sauce and Professor Restrepo and Jim Rickles collaborated on this. You can see here, there were 3 walls, 2 transversal and 1 longitudinal that was eccentric to induce some torsion in the response. Of course, this project would have benefited tremendously from a multi-degree of freedom shaking table. So you can see here a short movie of the response to an earthquake. This is a 40% scale building. And you see here a friction damper that was connecting the slab to one of the lateral wall, and the walls were rocking wall as well. You see here a short movie also of the capability with the soil box. You see the large laminous soil box here with a pile foundation in the middle here. You can see the building of the content of the box. The box is empty here. The pile is installed first, and then the soil. And then it was installed on a ramp because the soil liquefaction is more pronounced if, you know, the terrain has a slope. And you can see here the box that shows, you will see one of the layer is liquefying, and that's the one that gives you the largest shear strain. So in that region here, there is a gradual permanent deformation of the soil due to lateral soil spreading induced by soil liquefaction. So now let's talk about the 6 degree of freedom upgrade. So the 1 degree of freedom LH post had an accumulator bank of 50 bottle of 50 gallon, 2,500 gallon of nitrogen gas at 3,000 PSI. And during a test, we would push the oil at the bottom of this column to occupy about the 20% volume of this bottle in oil at 5,000 PSI. And then during an earthquake, we blow down this oil at 3,000 PSI and bring it to the 2 longitudinal actuators here. You see that we needed just one 12-inch huge pipe, 12-inch diameter pipe. Red is the pressure and blue is the return. And the vertical actuators, initially when we built the table, they were just pressure balance bearings. But in 2009, we already upgraded them as vertical actuators, but not ported with servo valve able to use them dynamically. They're only there to control the load pressure on the vertical actuators. So that's a picture that we already had in 2001. That's what was our vision for the future upgrade. We would add 2 horizontal actuators and put them in V shape, and we would add 1 hold down strut in the middle here. These hold down strut are pre-stressing the table against the vertical actuators to give the overturning moment capacity of the system. And we thought that we would just double up the accumulator bank. We had not done, you know, accurate simulation of the upgrade and so on. After doing this 2 years ago, we realized we needed much more than just doubling up the accumulator bank. So this is now the system that is being installed as we speak. This is the new accumulator bank, quadruple pretty much, 10,000 gallon instead of 2,500 gallon. And we need now 2 12-inch pipes pressure and 2 12-inch pipes return. We need a complete ring in the pit of the shake table. We need to go and feed each of the 6 vertical actuators, as you can see here. This is a close-up on the accumulator bank that now is almost touching the roof of the building, is huge compared to the previous one. We also had to buy 2 new pumps and more transfer pumps here. This is the surge tank. And you have a few figures from SolidWorks here, very detailed figures of the upgrade. You see the V-shape actuator, you see the vertical actuator. Each of them is now equipped with a huge servo valve, 5,000 gallon per minute. And also in the, so the east-west direction is the longitudinal direction, the transversal, we are limited to plus or minus 15 inches. Otherwise we would hit the vertical actuator with the platen or unseat the platen. So we have 3 lines of defense because the actuator can move much more than that in the transverse direction. So we need to prevent an impact of the platen against the reaction mass. And if we have 3 lines of defense, the third one being these big crash protection devices that you can see here. So you see also here the third hold down strut in the middle. This is the huge 5,000 gallon per minute servo valve that will be attached to each vertical actuators. These are now very important for the young investigators writing proposal. So now our peak displacement goes from plus or minus 75 centimeters to 89 centimeters, longitudinally plus or minus 38 centimeters, transversely plus or minus 13 centimeters vertically. The peak velocity was at 1.8 meter per second. It goes to 2.5 longitudinal, 2 meter per second, transversal, 0.6 meter per second vertical. The peak forces was at 6.8 meganewton longitudinal. It goes to 10.6, 8.4 transversal. And you see also the degrees, the rotation, and the overturning moment capacity. This is for a rigid payload of 5 meganewton here. And
Hello, Joel. This is Joanne Browning. I just wanted to remind you, we only have like a minute or 2 left if we're going to have time for questions.
Great, Joanne. Yeah, thank you. Let me briefly show a few more slides. We also have a modular test bed that is being developed. It will allow researchers to test building type structures without having to build the whole specimen. You see pictures here. They are developed by Tara Hutchinson, Gilberto Mosqueda, and Chris Pantelides from the University of Utah. It allows you to have all sort of configuration, frame configuration, brace frame, with the shear fuses for the moment frame behavior, buckling restraint braces, and so on. And I have a list here. I will be very brief, 3 slides, I think, of new, research made possible by the 6-degree of freedom upgrade. So we'll be able to investigate in 3D at large or full scale the combined effect, not only of translational ground motion component, but the rotational ground motion component as dynamic excitation to structural, geotechnical, soil foundation structural system, including SSI effects and nonlinear soil behavior, nonlinear structural behavior, and soil liquefaction. Rotational ground motion component have been neglected because we thought that they were not so important, but there are some publications that show otherwise. And now they will be able to, in the future, be measured during strong ground motions. Also the issue of understanding better the inherent damping in structural system with targeted experiment with 6-degree of freedom table should be able to enlighten much more this topic. Also dynamic soil structure interaction can be done, in different ways that are listed here. I'll provide, I guess, the PDF of the presentation. You can look in more detail here. And real-time hybrid shaking table system to push the complexity of the large-scale, hybrid testing on shake table. It's very challenging again. And seismic response behavior of unreinforced masonry and reinforced concrete and reinforced masonry structures. Most of the design code are basically based on in-plane behavior, in-plane excitation of walls, for example. If you have biaxial, horizontal, and vertical, this changes the picture drastically in some cases. So, and non-structural component and systems, there is a need to improve our understanding of how they respond to multi-directional earthquake excitation so that we can develop a reliable and unified design strategy to account for that. and damage-free, maintenance-free earthquake protective systems, accelerated bridge construction, for example, to investigate the behavior of the pretty complex kinematics that these systems require under multi-directional excitation. And this gives here a list of people to contact for help with the planning your proposal and question with your proposal. We have 2 upcoming workshops, a joint academia industry workshop in the fall. The date is not determined yet, will come very soon. It will be virtual, and then a joint workshop with the NHERI Rapid facility and most likely the SIM Center as well in December 2020. So I want to acknowledge NSF and thank you for your attention. This is a rendering of the first specimen that will be tested after we reopen in May. We were supposed to reopen early April 2021. We are 6 weeks late because of COVID. So if it stays the same, we will open in mid-May 2021.
And we have one question to start. How early in the proposal process should a PI reach out to your facility?
This is for me, Karina, or
This
for
is
everyone?
Yes, for any of the sites. How early should PIs reach out to your facility?
Oh,
Maybe
sorry. Go ahead, Joel, if you want to talk. This is Jim. Sorry.
Yes, I would say in our case, because of the size of the specimen and make sure that the specimen that is planned, will be testable, so to speak, on the shake table. It's very important to talk with our team early on. And usually the team that develops the proposal, they already do some simplified model of the specimen and simplified simulation. And so checking all of these with our site and also the construction of the specimen to bring this up early on is important.
Yeah, I think our experience has been the earliest, the better in terms of talking with either technical or non-technical. There's logistics, there's budget aspect, what's paid for, what's not paid for, what's possible. I think before you put the pen to the paper, and at our site, we have some checklists that the researchers can go through. It's on our website. And I think that's the very first thing researchers should consider looking at that are interested in using possibly the facility. Then they could proceed and contact us. And when they contact us, things remain confidential. We don't share other people's ideas. If you sense that perhaps there's a faculty at Lehigh, such as myself, may have a conflict of interest, we avoid that. I don't need to participate in those discussions. The other development and research engineers are technically competent. So the earlier, the better.
Yeah, the same would go for us. Earlier, the better. And same thing if you have concerns about talking with other faculty members about your ideas. That's why our first point of contact is our operations manager. And if you need to bring on other people, you can. We have the added piece of being in the field. So identifying the proper locations for your testing is important to get done earlier, so we can start the process of looking at permits to access the location or look at alternative locations that might be better suited in terms of accessibility, but still meet your research needs.
Thank you. We have another question. This is for UC San Diego. What is the typical project duration from proposal planning to testing? And specifically, how far ahead are tests on the shake table scheduled?
Yes, so, typically when people use our site, when they are funded by NSF, they probably take at least 1 year to start, define and refine the design of their specimen. And now, if you think that to write the proposal, it takes 6 months to have it reviewed by NSF. So it means by the time you submit your proposal, probably it will be 1.5 years later that you will come to the site and start the construction. And I forgot, and the duration. The duration goes from, a few weeks, but usually commercial project, we had a few of them over the years. They are very fast, a couple of weeks. But we had the research project is, the short one are more like 2 or 3 months. And the very, very long one, like the 5-story full-scale building, was a year from the time we started building the specimen until we dismantled it from the shake table platen. And there was one more question, I think. Right now, when we reopen in May 2021, we will have this large 10-story heavy timber building that will occupy the table probably for the rest of 2021.
Thank you, Joel. We have one final question. How would participants, sorry, size-wise, what was the smallest test conducted and how long did it take? This is for Joel.
Oh, for San Diego, the size-wise?
The smallest test conducted and how long did it take?
Well, probably was Gilberto Mosqueda when he did the commissioning test for hybrid shake table test with a couple of concrete slabs on 6 seismic isolators. And he was able to do this in a couple of weeks. So again, he was assuming that these slab with the isolators were on the roof of a building, and he would model the building in the computer and connect both of them, in real time. So this took a few weeks. That was the smallest test that I can remember. Otherwise, if it was a specimen, with outside of hybrid testing, it was I forgot maybe which one, but at least 2 or 3 months.
Good morning, everyone. I hope your morning is going well. I will be talking about the centrifuge modeling facility at UC Davis. Let me give a brief introduction about myself. I am a PhD candidate at UC Davis. My research involves liquefaction-induced downdrag and soils. I did a couple of centrifuge tests investigating the development of downdrag on piles and liquefiable soils. Some of the other projects that I was involved and helped with are the snake skin piles, characterizing the monotonic and cyclic response of them, a Becker penetration test, looking at the dynamic response of the Becker pile with a newly devised pile hammer that we just have at the centrifuge. We just upgraded at the centrifuge, and the recent validation LEAP 2020 tests on a retaining wall subject to earthquakes in liquefying ground conditions. These are like a video of those experiments performed. So in today's presentation, I will be basically talking about a brief introduction of principles of centrifuge modeling. Then I'll talk about our facility, the vision and objective, and some examples of centrifuge experiments and how does centrifuge work. And following that, I will talk about how can you choose between the different centrifuges that we have here, how can you develop your schedule, and how can you estimate the budget for your test. So most civil engineering systems and infrastructures involve some kind of interaction with the ground and in the soil, with the structures and the fluid in some way or the other. So for example, structures transfer their weight to the soil. Earthquake involves coupling between the soil and the structural system. There could be fluid pressures also involved, which interact with the soil stresses. For example, you can look at the city where there are different structures. During an earthquake, they can interact with each other. If you go very detail, you can look at soil foundation interaction problems in offshores because of the moving of the turbines, the wind turbines, you can generate cyclic loading within the soil. And then there are other hazards like liquefaction or flow failures that could occur in soil or different materials that are contained within structures. So overall, we want to understand the mechanical response of the soil in many of these cases. So just let me give you a brief introduction about how the soil behaves and why we need to have this kind of modeling approach. So soil can be considered as a frictional material, which means it gets its strength from the friction. And as we know, friction depends up on the normal weight. So if we go deeper within the ground, we get more normal load, and thus we get a more friction. And the response of the soil, which is a frictional material, thus often depends upon the stresses that is induced within the soil. So in order to get the correct response, deformation, the stiffness, and the stiffness, we need to get the correct stress behavior. So what does that mean for scale modeling? So if you want to model a full scale model of, let's say, a foundation in the soil, and if we take a scaled model of that, a reduced scale model of that, the only way we can model this problem and get realistic deformations is only when we can get correct stresses within the system. And since in a small model, we have less normal force, the only way we can increase the normal force and thus the stresses within the system is by increasing the gravity. So that's what is done in the centrifuge modeling. The idea is to produce realistic stresses and realistic stress distributions in a controlled environment with well-defined boundary conditions and well-defined material properties. So what we do is we take this small reduced scale model, we spin it in a centrifuge, and with this centrifugal force, we increase the vertical gravitational force acting on the model, and that's how we increase the stresses that act in the soil and within the structure. And that's how the response then that we get is the correct response that we want to actually model in our prototype problems. So when we talk about scale model test, often comes different scaling factors, and the same is with the centrifuge modeling. There are different scaling factors for stress, density, length, gravity, and many of the times for a specific test that you are interested in your research, you need to make sure that the scaling laws are properly valid within that physics of the phenomena that you're interested in. Often it is advised when you're writing your proposals, it is suggested to justify those scaling laws so that the reviewer can be well convinced and knows. Many times the reviewer might not know those scaling laws, or you need to convince those scaling laws, and it's suggested to be addressed in your proposal. So just keep that in mind. Now talking about the centrifuge facility, our operational vision is to provide an open and equal access to this world-class facility and help people to write proposals to the NSF to use this shared resource. With the scale modeling of systems, it enables major advances in ability to predict and improve the performance of soil and structural systems. So we have two different facilities at UC Davis. One is the 9-meter radius centrifuge, which have a bigger area and you can test bigger problems which have interactions with soil and the structure. And we have 1-meter radius centrifuge, which is comparatively small, but at the same time is less costly, and you can do many tests in a small, in a defined period of time. So both of them have their own advantages, and depends upon your project which one you would like to use, and also the type of problem you are addressing in your research. We have 25 years of expertise in managing this shared resource. Our current director is Professor Ross Boulanger. After our past director was Professor Bruce Cutter. Dr. Dan Wilson is the current CGM Associate Director, and he has been here managing the facility for the past 20 years. And we have Professor Jason DeYoung, Professor Katrina Ziotopoulos, and Professor Alejandro Martinez as our CGM advisors. And as this facility is not complete with our skilled and experienced staff, we have Tom Conkey, Chad Justice, and Anatoly, and Mary, who help in each of the projects by having their specific roles, which is listed here. Here are some of the examples of some of the centrifuge tests. This is a very interesting and very unique example where researchers use the two different NHERI facilities for the specific part of their research. For example, in UCSD, the experiment involved two 1.52 meter footings where the structure, the structure had very much detailing and was performed in a soil depth of 3 meters. So the response they got from that was used to get a very detailed response from the structure, whereas in the centrifuge, you can model the soil depth up to 22 meters, and obviously the structural was not much as detailed as it was in the UC San Diego experiment, shake table experiment. But now you could place different footings, like 6 footings, as you can see here, and see the soil foundation interaction. So as a researcher, you can think of different NHERI facilities and how you can use those facilities for looking at the specific aspect of your research. Here are some other examples. On the far top left is a rocking foundation example. In the middle top is a bar tube example. This is an excellent example of collaboration between research and industry. BART actually wanted to remediate the BART. The city wanted to remediate the BART because they thought that during an earthquake, the BART would flow and there could be damage to the BART. And Fugro, which was the company who was actually providing consultancy to the BART, actually did some numerical models and showed that it was not a problem and the remediation was not necessary, although they were not convinced. So they came here and conducted a centrifuge test and find out the flow mechanism, the failure mechanism, and convinced the client that the remediation was not necessary, and it saved tens of millions of dollars. So that was quite an interesting use of centrifuge facility in order to validate the failure mechanisms. Some of the other examples are ground reinforcement, offshore structures, a city block experiment. This is another very interesting example which involved PIs from different universities, and this is an example, a great a type of projects that you can do with large centrifuge test. So it involved complex structures, lots of instrumentations, and it was mounted on the centrifuge, and the interaction between the different structures and the soil was investigated. So this is one of the biggest advantages of using the big centrifuge facility where you can have many elements and study their interactions. On the right is the study of the weak drains and how they used to dissipate the pore pressures during an earthquake. And this experiment was performed in the small 1 meter radius centrifuge this is again the city block example, and on the top left shows the actual real-time model during testing. When you are testing in the centrifuge, actually the time, as you spin up and increase your gravitational level, the time reduces by the same factor. So that's why the earthquake, which is, let's say, 30 seconds, if you spin at 30 Gs, becomes 1 second. So that's how fast actually you see, you do the test in actual. And on the bottom right is the scale time for full size system. And now you can see the movement of the structure with respect to the soil during an earthquake. So also recently we have been testing beyond earthquake hazards. We have recently tested wind and wave loading of offshore turbine foundation using small centrifuge. We also recently tested centrifuge modeling. We did centrifuge modeling of tsunami-induced soil structure instability with collaborations from Oregon State University. And again, recently, we also did stability of partially saturated fly ash impoundments, investigating the runoff behavior of byproduct of coal and combustions. And it was a collaboration between NHERI and UC Davis. Now, often these complicated and large tests involves sensing capabilities. As far as the sensors are considered, we readily provide these sensors within our facilities, which are pore pressure transducers, accelerometers, benders, linear potentiometers, MEM accelerometers, high speed and high resolution cameras. We just bought we just upgraded to these high speed and high resolution cameras, much more beyond GoPros, where now we can go up to 20,000 hertz frame rate, and we can get 4K resolution video. Also, we recently bought a handheld 3D scanner, which could be used to get more in-depth readings or profiles of the models that we do. In terms of soil strength testing, we do cone penetration test, T-bar test, and wind shear test in flight. And many of the times, the projects they come up their own sensing sensors, and because they have their own specific physical things that they want to capture. And some of the examples are, like for my test, I had a pile with multiple strain gauges installed inside the pipe of like 15 millimeters. I used lasers and camera to measure the settlements of the soil and the pile. We have used text scanners to measure the soil pressure or the water pressure, dynamic water pressure occurring during the experiment. Recently, past year, researchers from UIUC and University of Vermont did a test on a coupon, which was embedded inside the soil, which was connected with the wire to the motor and pulley system. And they pulled that coupon during an earthquake when soil liquefied to measure the shear strength of soil. So as a researcher, you can go with the other sensors that you want to use in your test, and we provide support to integrate those special sensors that you would need for your test to our data acquisition system, so that everything is in synchronous to our testing, so that all the data that you get is synchronous. So in terms of how centrifuge works, this is a model of a 9-meter centrifuge. It consists of a 9-meter radius long shaft fixed on an axle, and it moves. And on one side of the shaft is you have this a bucket, we say as a bucket, where you place the model container. So here in this picture, you see a model container. This container shown here is a flexible container, which can go into shear during an earthquake. And it's quite useful when you are modeling an earthquake behavior and you want to have shear in your problem. We have other types of containers like fixed containers, rigid containers. We have transparent containers if you want to look at the flow of the soil within your model. Often researchers also come up with their own containers. For example, for the tsunami centrifuge test, they build their own container. Similarly, for the fly ash impoundment project, they build their own container. We also provide support in building up the containers for the respective tests. On this bucket, we have data acquisition system, which is shown here and right also on the front. And the bottom of the container is the shake table, which is used to shake the model and generate earthquakes. So in order to reach the correct stresses, the centrifuge is spinned, and when a high RPM is achieved, let's say 90 RPM, the bucket becomes almost horizontal, and then the centrifugal force acts on the model and increases the gravity, and the stresses within the soil or the structure reaches the same as the prototype scale. And at this point, we can now do our static tests or dynamic test by shaking the model, and then the sensors are used to like capture the response, and then we spin down and take our model and then dissect it. So that's how like the whole process of running a centrifuge test, and that's how it works. Now, in terms of planning a centrifuge test, since we have two facilities, a small centrifuge, a large centrifuge, it is important to identify what kind of projects you can run on the small centrifuge. A small centrifuge, you can run a small, oh, it's already 18 minutes. You can run projects in which there are no boundary effects, and where you can investigate some mechanisms or like mechanisms which does not involve so much interaction. For example, here is the reinforcement effect of soil cement columns that was done on a small scale centrifuge. And then again, this is a Bart's cube, which involved a much more complicated soil profile and geometry, and was performed on large scale centrifuge. And this is how the team looks like. A small test, a simple test would look like something like this, and a complicated test like the city block would look something like that. And just to remember, always on your team, you have the staff with their expertise who would be helping you at each and every step during your experiment by providing the expertise to the test. This is how a real project looks like. As a researcher, you would be as like a graduate student who is working on the project, is the project manager who is managing between the staff, the resources and everything, and the PI, principal investigator, is on the top, managing the graduate student to take those decisions, and Dan Wilson, who is associate director, and Ross, who is the director, becomes the co-PI, advising on the different aspects of the centrifuge test. So this is how a user's journey would look like for our facility. So in the initial phase, when you are making a proposal, we provide support and advice on the test plans and the cost aspect of that. Once the proposal is ready and it has been finalized and it has been approved, the users come to the facility and then construct those components, construct the model, do the centrifuge testing, and then dissect the model. This takes about 1 to 3 months, depends upon what kind of centrifuge you are using, whether you are using a small one, which is comparatively easy to conduct and takes less time, whereas the big one might take 3 months. At this period of time, we provide support through our staff in all of these activities. Once that is done, the other part is then data. We also provide support in data archiving, interpretation of the data, and reading the data by providing some tools. And so that reading the data and interpreting it, and they again designing a new experiment and testing it again usually involves 1 to 6 months. So overall, you are looking at 2 to 9 months of time frame between two tests. So just keep in mind while you are making a proposal that. And the last part is the budget planning. So we are generally, the centrifuge operates as 200 miles per hour, and it's a large piece of equipment, which is very complicated, and thus it has relatively large operational cost compared to other facilities. And overall, the cost can be separated into 2 categories. One is inside the box operations, which I have shown here, and the other is outside the box operations. So inside the box operations consist of all the activities that we generally would like CGM to do, because those activities are critical activities, and if something goes wrong, that could actually do something bad, or that could actually make the facility damage the facility. So all of those activities we do, and all the other activities that are non-essential are done by the researcher. For example, applying the strain gauges, building the model, moving the cameras, and all of that is done by that. Now, many of the times we receive emails asking about the cost of the centrifuge project. What we have done is we have put the spreadsheet on our website. If you go check on our website, where you can find the cost regarding different parts of the test, and you can come up with a rough estimate, and then we can talk from there. In terms of like the cost, just to give a brief idea, for NSF projects.
This is Joanne Browning. I just wanted to let you know you really need to wrap up in about 30 seconds if we can.
Sure, yeah. And
thank you.
Yeah, in terms of NSF projects, some of these inside of the box operations is taken care by the NHERI. For non-NSF projects, it's not covered, and this is has to be included in your budget. We have our Facebook page, and we have all of those resources on our website. Please go and check it. We do provide, we do workshops every year like other NHERI facilities, usually in spring quarter. You can find our previous workshops and related resources by going to the NHERI facility and this workshop tab. So please go and check there. And this is a summary of what I talked today. Please feel free to check our websites. Our contact person is Dr. Dan Wilson, who is Associate Director. You can reach out to this email ID. And thank you for listening to the presentation. If you have any questions, do let me know, and I will answer it during the question answer session.
Good morning, everyone. My name is Pedro Lomonaco. I'm the director of the Hinsdale Wave Research Laboratory at Oregon State University, and co-PI with Dan Cox and Kurt Higgins with the NHERI Experimental Facility at OSU. What I'm going to be presenting today, if these hints work, which is, okay, there you go, is we are going to talk about a little bit on the story of the facility, our, very briefly, our capabilities, what you can do here, and the description of the experimental facility, a little bit on the user support that we provide, and also some examples. I'm going to go through those real quick to see some examples to try to foster your imagination and do some testing at Hinsdale. The facility was established in 1972, so that is already 48 years ago. And since then, well, you can imagine, well, the facility has grown and has changed significantly. You see some pictures there. Well, the first facility, the Flume, was an outdoor facility. You have some testing in the snow. We have protection, so you don't have to do that anymore. And since then, well, all kind of studies have been done in the facility with what we have right now. This is how it looks like right now. We have two buildings. One hosts the large wave flume, and the other one hosts the directional wave basin. And I'm going to talk about on the details of those in a minute. What type of studies can you do here? Well, you name it. Imagine the both facilities are basically two open boxes. And there we adapt and construct models and perform experiments based on the different needs. So we go from nearshore hydrodynamics, tsunami studies, coastal structures, sediment transport, environmental fluid mechanics, which is transport and mixing of pollutants and other processes, floating structures, and here, for example, some images of different type of testing, just to give you an idea of the type of things that we have done. And as I'm saying, after 48 years of testing, well, what we have done is anything you can imagine that goes into the water, we have probably already tested. Including floating obstructions, yes, of course. So since 2004-2014, the experimental facility was part of the NIS network, and since 2016, the laboratory is an experimental facility of NHERI, as I mentioned, and also the facility is affiliated with the Pacific Marine Energy Center, which is fundamentally for marine energy studies. So what do we have at Hinsdale? We have two major resources and 4 facilities, the large wave flume and the directional wave basin. And so how do they look like? Well, the large wave flume is fundamentally a very long canal. Again, is a tank. Normally is just a prismatic open tank. And then on top of that, we can build and install different kinds of models and bathymetries and different structures. Let me see if I can run this. This is just an example of one of the experiments that we have done, and showing also our outreach program. We have every year between 5,000 and 8,000 students from different ages to see how we do the experiments and trying to foster also their interest in science and engineering. Let me just, sorry, I have to. The center is what we call the performance curves of the flume. Those curves shows you what are the wave height capacity in the flume in relative to the wave period of the waves we can generate. And you see that each of the curves have 3 distinct sections. One of the section is limited by the steepness of the wave. So in this case, from 0 to a little bit less than 4-second waves. Those are waves that are limited by wave breaking. So that important message there is that any wave that is above this curve is physically impossible. So it's just the wave is just too steep, and in nature will never happen. This limitation is a limit that depends on the water depth and the generation of the interaction, how we generate the waves in this case. And what we call this is shallow water conditions in terms of capacity. And this section at the end is limited by the stroke of the wave machine. So as you can see, for example, for different water depths, in this case, for example, 2.7 meters depth, we can generate any wave that you see that is under that curve and that combination. And that is why we call it the wave height performance, because that is our system capable of doing. This is for the basin. The basin is again a prismatic tank, and the fundamental difference between the flume and the basin is that the flume is fundamentally 2DV, so it's 2-dimensional vertical type of structure and testing facility. So we generate waves in one section, and then that propagates along that canal, the canal. In the basin, we have we just free the 3-dimensional component. So we can generate waves, and we can have models which has 3-dimensionalities. And it looks basically like a swimming pool. We don't call it swimming pool because we cannot swim over there, but it's fundamentally like that. And in terms of size, it's very close to an Olympic swimming pool. So let me show you this video. Again, this is an example of a tsunami wave propagating, and we were studying there the effect of this wave as propagates over the shoreline. Again, the curve on your right-hand side, the top right, shows you the performance of the facility. And if you more or less would like to compare the capacity of the flume and the basin, the basin can produce about half of whatever we can produce in the flume. In terms of size, as previously we have seen in other facilities, of course, our experimental facility cannot necessarily produce a full-scale conditions. Sometimes yes, but most of the time is we have to reduce the scale, and that introduces some important parameters that we have to bear in having consideration, which is the scaling effects. So in that sense, when we do the scaling, we follow fruit scaling, which means that we assume that the inertia forces and the gravitational forces are dominant. And in that case, we take care of considering the changes in the forces and the masses and time and so on. But that means that if we are doing things too small, then we end up having some limitations in how we reproduce and represent nature. So that's why we want to be as large as possible in all the cases. We want to have large scale facilities for doing the tests, and that's why these two facilities are fundamental for that. This is the way we represent is similar to previously we saw in the centrifuge, how we support the users. This is the path of somebody who is preparing a proposal to use the facility. So we have a number of users observing, like you right now are observing what we do in the experimental facility, and then that triggers your interest in doing some research, including the facility. So as you see during the proposal preparation, so already in this stage, we recommend, as also was mentioned before, that the experimental facility gets contact with you, because from that early stage, you will have a very good our support in terms of understanding what are the processes and other elements along the proposal preparation. So as early as possible, if we would like to get in contact with you and support in your proposal. Then you submit your proposal to NSF, and once you get the award, then this is what we call our research path. It was shown in the centrifuge as a highway. Well, this is in our case relatively simplified. And also during that process, there is a continuous communication with us, which is how we schedule the testing in the facility through the NCO and our own calendar. And also in the design, we support the design of your testing, and that is also part of our support during the whole duration of your award. Once we have the testing happening in the facility, well, this is the sequencing of all the different activities that should happen there until you get the experiment. At the end of the experiments, the outcome of that is the information, the data that goes back to we will be uploaded in the design safe, and also it's included in the cloud, and that comes back to you pre or post process, so you can start doing the publication and discoveries, and that includes the process of the research you are doing. Just a few examples. I'm going to go really quick and with some of the projects that well, all the projects that we have done at Hinsdale since the beginning of NHERI. But the structure of all these slides, you will notice is not only the description and the PIs of involved in the project and what we have done for that, but also is getting a little bit cluttered already, because that includes not only the objectives and aims of the project, but also that includes what have been publishing related to or has been published related to these projects. So this is a study on the effect of the air gap, so the space that is underneath coastal structures when storm surge and waves are hitting coastal structures like building, houses, or hospitals. This is a study that was done all the early stages of NHERI. This is a study on the effect of offshore islands on the propagation of tsunamis. It was done in 2 phases. You will see later on how we did it, and different types of instrumentations that we have done. The research question here is whether if you live in a coastline that you are protected by an island, the question is, are you more prone to have larger run-up or larger effect of the tsunami or not? And we tested different shapes of islands, and we found that in certain conditions, the effect of the island is actually what it's doing is actually enhancing the tsunami in some situations. This is another project that we reutilize some of the testing rig that we were using. In this case, probably you don't see it, but we have some stilts. So these are the classical houses on stilts, and we were studying the effect of tsunamis and forces on that. Well, in this case, we were studying the effect of sheltering, so macro roughness effects of different other buildings and how that changes the forces and hydrodynamics around it. And also we included some preliminary experiments on debris effects on the structure and the impact forces and transport of different shapes and quantities of debris hitting that structure. This is another story, a study on the effect of waves and forces on fuel tanks located at the coast, in refineries, on ports. And when you have an earthquake, or you have a tsunami, or you have flooding and a storm, what are the forces and what was the study in the interaction between different the fuel tanks between them and in the hydrodynamics there. This is a very interesting study done by a company that has an SBIR a project through NSF, and they developed the system of the self-deployable walls to protect the coastline against storm surge and tsunamis. And we were studying, if you see in this case, in the two facilities, in one case we were studying how the system worked and how was watertight in terms of keeping itself against the flooding, and also we were studying its resistance against the different forces of waves in the flume. This is the second phase of the island project, the Tsunami Island project, and we were studying different ways of measuring the flow around it for calibration of a numerical model. In the flume, we also tested the forces, the impact forces of waves on offshore wind piles, and basically what we didn't have to represent the full offshore wind. It was just basically the foundations, and we were studying different conditions of tsunamis and waves breaking on the structure. This is another study on the effect and on how the rip currents were formed in the basin, and we had to use the very specific type of measuring. In this case, we have to cover completely everything in the basin. This is during the summer, and it was during the day. You see, it was completely covered everything, so we can measure the wave conditions here with cameras and infrared system. It was a very complex system developed by UW, University of Washington, to measure with lasers and infrared cameras the conditions here, the free surface, and also the currents on the coast. This is another story in the flume. The study was on the generation of what we call in the Pacific Northwest the sneaker waves. Is the generation of abnormally long or large run-up events produced by the propagation of groups of waves in the coast, and that typically creates a hazard to the people. It typically drowns, well, not typically, but it drowns approximately in average between 1 and 2 people every year, and it creates problems on safety on the beaches, especially when during the tourist season. People don't necessarily know what to do with these events, and it's a common situation that happens in all over the world. Is in different countries in the world have the same situations. This is another study, completely different as the others. This is the machine that was developed by Dr. Fritz on sorry, it's just my phone is talking to me. So it's a machine that generates underwater volcano eruptions, and this machine was created to control the generation of the eruption of the volcano. So in this case, what you see at the background is the weigh machine that was not used in this case. It was just so use this machine, which is the volcano eruption generator. It created during the underwater eruption. It created a tsunami, and we measured how the tsunami was propagating. The interesting thing that happens is that at the end of this study, it was the tsunami in the zone of Krakatoa in Indonesia. Created a tsunami that nobody was able to measure until it hit the coast and killed hundreds of people, and it happens just at the same time, and it was just showing that whatever we know on the generation of tsunamis for underwater volcano was not, it was just starting, and this project happened at the same time. This is a significantly complex project that we did last year on the overland flow. So we have a different combinations. I'm going to show a bunch of images that, because we did a lot of things here, with were 5 PIs involved and 2 different countries. We have people coming from Korea and Japan also during this experiment. So fundamentally, what we have, it was in the basin, we modified the bathymetry. We created a section at the center for doing some testing, and then we have the other section of the compartmentalization of the basin to create currents, and we did experiments with overland flow. So that was continuous current, waves, and tsunamis, and we study effect of macro roughness. We study the protection with seawalls and submerged breakwaters. We study the effect of mangrove and how it was protecting it. We did studying hydrodynamic studies with dye advection and debris representing the destruction of a pier. We also study how was the different pieces of debris was propagating against those coastal structures, and then we blow this scale up to the case of a full, well, it was a 1 to 6 scale of a fully constructed, structural constructed system, and it was tested until it was completely damaged. So this is one of the, during this project, we did some, it was the opportunity to do some payload project with another
This is Joanne Browning. Sorry
Yes.
to interrupt, but we are running a little over. If you could wrap up in the next minute or so.
Yes, of course, no problem. Anyway, so we have some experiments with a payload project with the U.S. and Naval Academy, and we did some experiments on the effect of a patch of mangrove in the basin. So different aspects of the studies that we were using with the same facility, which was extremely complex and large, and which included also a study of that we used the same layout in the bathymetry for studying the effect of storms and storm surge and storm waves on the destruction of houses. And you see, for example, the house that is not done still was destroyed. It was the mechanical properties of those houses were included in the in the study. And another super large project that we did last year was this study on the effect of vegetation to protect sand dunes. And again, you see, well, there is a pretty complex on the different things and the number of instruments we did, but we built actually a dune there with 1,000 tons of sand that we included in the flume, and we put some vegetation too, and we let it grow over the a time frame of five months. The last project we were doing, it was a study on vertical evacuation structures, and we are still, this is a project that is still ongoing, and we basically we're gonna test a different type of structure to see the effect of the forces on tsunamis hitting on the structure. And this is just a summary of the and different things that we have done in terms of projects, a number of institutions and users and the publications and other outcome of the project. And with this, I'm good. Thank you.
So hi, everyone. As Karina and Joanne said, my name is Lori Peak, and it is an honor and pleasure to be with all of you today. I serve as the principal investigator for the NHERI Converge facility, which, as you saw on the NHERI wheel, is the most recently funded NHERI facility. We were established in August of 2018. And so we're nearing our 2-year anniversary, and it has been an absolute honor to join this NHERI network as the first social science-led component in that NHERI wheel. And I am so excited to share with you today. So first, I want to offer gratitude to the ECO as well as the NCO, and especially to Karina and Joanne, Julio, Cheryl Ann, the entire team, Dan, who are constantly working to bring researchers together to train and mentor a diverse next generation. And I especially want to thank all of the participants in this Summer Institute today. I know we're not able to gather together in San Antonio, but I am so pleased that a larger number of you were able to participate in this online version of the Summer Institute this year. For those of you I already know, it's great to see your names. And for those of you I don't know, I wanted to start by saying a little bit about my background and what I do. And so this is where I live. This is Boulder, Colorado. For those of you who haven't been here, we hope that you're going to get to join us one summer soon at our natural hazards workshop or at our researchers meeting or at some other event. We have fantastic engineering and social science programs here at the university, as well as many other programs. So that's where I live. But I want to tell you a little bit about what I care about. And so I really appreciated that Karina invited us to introduce ourselves at the beginning of this session. And I want you to know that some of the big things I care about in my personal and professional life are reducing social and economic vulnerability, to reduce the vulnerability to natural hazards, trying to recognize and encourage people's capacity, and also bringing together researchers in order to try to respond to the pressing challenges that we face. And so that's why I'm so excited to join all of you today, and also to be involved in many other early career, student-centered and early career faculty-centered mentoring programs like the Minority Surge Project. So today I'm going to be using my time to share with you about the NHERI Converge facility. And so the Converge facility is really dedicated to 5 major tasks that I'm going to walk you through today. So task 1 is related to identifying researchers, task 2 to educating and training researchers, task 3 to setting and promoting a convergence research agenda, task 4 to connecting researchers to one another and to NHERI resources, and to coordinating diverse research teams, and to funding convergence research and implementation. Now, to all the participants on the call, I'm going to need to ask that you please continue to listen, because I've actually embedded questions for you throughout this presentation, because I, as well as the leaders of the networks that I'm going to be talking about, are very eager to learn from you today. So, first question, we would like to know, and will you please put this in the chat box, have you ever conducted post-disaster field reconnaissance or research after an earthquake, after a hurricane, after a tsunami? Ian Robertson, I saw you on here. And so this is not just for the Summer Institute early career faculty and students. If you are on this call, please go ahead and respond. Have you ever conducted post-disaster field reconnaissance? And I'd like to tell you all while you're chiming in, I've had the gift of conducting field reconnaissance both by myself in small teams of social scientists, but also as I've progressed through my career, increasingly in teams with engineers, where I've learned a great deal. So thank you. Question 2, regardless of whether you have or haven't conducted post-disaster field research, will you please now respond, question 2, are you interested in joining a disciplinary or multidisciplinary disaster field research team at some point in your career? And so again, just a yes, no, or a maybe would suffice. And thanks for chiming in. I can see the chat box lighting up. So the second question about if you are interested in joining a field team leads me to the first area of what Converge is all about. And so as you saw on our graphic depicting what we do through Converge, step one is about identifying researchers. And that's no small task in our hazards and disaster research field. We're a large, global, multidisciplinary research community that's growing by leaps and bounds each year as are disaster losses. And so over the years, one of the things that NSF has done is NSF has invested in what we refer to as the EER, or Extreme Events Research and Reconnaissance Ecosystem. And you can see a graphic up there depicting the 7 currently funded extreme events research or reconnaissance networks. And so a question I'd like to ask you out there on the call, question 3, will you please say which EER is closest to your disciplinary background? And so if you're a social scientist, you would likely put in SCER. If you're a geotech, you would put in GEAR, most likely. If you're a structural engineer, and I know we have plenty of structural engineers out there, you'll probably put in STEER. And we also have one of the leaders of STEER on the call, Ian Robertson. If you're a nearshore scientist, place in NEAR. If you're an interdisciplinary scientist or engineer, put in ICEER, and so on. Thank you again for chiming in. So this is the first step of Converge, is that while each of these EERs have their own principal investigators, they each have their own mission. Under the Converge banner, we have had the opportunity for the first time to bring together the leadership of these EERs so we can work together to move forward on our second major task, which is to educate and train a diverse next generation of hazards and disaster researchers. And so now, to everybody on the call, I'm just getting ready to share with you a series of free resources that we've either developed through Converge or in partnership with the other facilities to try to help get the next generation ready to conduct post-disaster field reconnaissance, but also to conduct disaster research across the life cycle, whether you're looking at mitigation or recovery. And so one big thing that we do through Converge is we've developed a series of free online training modules. They take about 30 to 60 minutes to complete. They're highly visual and interactive. In fact, last summer, 27 engineering undergraduates who were at the various NHERI facilities, thanks to Karina and Joanne, became our first testers for our first module. So these modules are interactive, they're meant for a diverse disciplinary audience, and they're great for classroom assignments because they can be completed in relatively short order. So you can log into our Converge website and you can access, or you can assign these training modules. We've also been developing, for those early career faculty out there who may be desperate for new online assignments, we've developed a free online assignment bank where you can go and see how other professors are using these Converge training modules in their courses. When your students or you are done with completing the module, you'll actually receive a signed certificate of completion, and each module has its own certificate of completion, and there's a quiz at the end that's on a rotator, so you can assign this to a class and your students won't get the same questions. And eventually what we're trying to move toward is a credentialing system to ensure that our hazards and disaster field has a bare minimum level of ethical and research competence. We also have a series of extreme events research check sheets that are all free for download on our website, that you can go and access those and get some quick and usable resources for how to get ready to conduct disaster research. We also have a data tab on the Converge website that I hope can be helpful to many of you. And so if you're planning on writing an NSF grant at some point in your career, or for those who already have, you know that one of the things you have to do is to write a data management plan. And so in partnership with Design Safe, we actually have draft text up there on our Converge website to help you to write a data management plan. We also are getting ready to host, in partnership with Design Safe and Rapid, a publisher data event for social scientists to help them to learn how to use Design Safe and their resources. And we're hoping to have broader events in the future that bring together multidisciplinary groups so we can learn from one another about the data types that we use. We also have partnered with the Rapid facility to advance mobile data applications, and with Design Safe to advance their extraordinary field research model that you're going to hear more about today. Now, our third big area within the Converge facility is related to encouraging conceptual integration across disciplines and promoting convergence research. And so I'd like you all to please look at this graphic, which is in a recent article that we've just published as part of a special issue on NHERI. And I want you to look there, and I want you to look at sort of what does unidisciplinarity mean in terms of depth of knowledge, multidisciplinarity in terms of maintaining your own disciplinary identity, but beginning to build teams together, interdisciplinarity, and transdisciplinarity. And then, fourth question, when you look at that graphic, everybody out there, will you please put in the chat box, which of the following best represents the research that you currently do? Are you mostly doing single discipline, unidisciplinary research? Are you in the multidisciplinary box? Have you moved into an interdisciplinary space or transdisciplinary space? So please go ahead and chime in there if you would. Thank you. And I'd like to say to all the early career faculty out there, if I would have responded to this in 2005, I 100% would have said unidisciplinary. I was very much clearly in my sociology lane, but over the years, I had the chance to collaborate with engineers and have increasingly been moving across those degrees of conceptual integration, thanks to the things that I have learned from my engineering colleagues and the things they have taught me, and I hope in turn, the things that I have been able to share as a social scientist. So now, fifth question, everybody. Which of the following best represents the research that you want to do? And so where do you want to go in your career? Do you want to stay? And there's not a right or a wrong answer. There's not a good or a bad, but this is something that's very important for you to think about. Because, for example, as you're going to hear this afternoon, if you're going to write a career award, you're going to really have to think about this. Do you want to stay in that depth of knowledge and do advancements with where you're going? Or is your hope that in the future, you're going to collaborate and move into a different degree of conceptual integration? And so please take a look at that, and if you would, let us know where you want to go. Thank you. Okay, now, so why are we doing this? 3 reasons why we are promoting convergence research through this facility, and it is integral to what we're doing at Converge. Number 1, NSF is encouraging it. For those of you who've been following the NSF 10 Big Ideas, you know that growing convergence research is one of those 10 big ideas where the foundation is prioritizing funding. And so it's very important for you to understand if you are going to move forward with applying for a convergence research grant, for example, how NSF is conceptualizing convergence, as it's about that deep conceptual integration, but it's also about research that's driven by a specific and compelling problem. Second big reason that we promote convergence research through our facility is because our field demands it. Disasters, if we're really going to achieve our goal of reducing disaster losses and of promoting collective well-being, it is absolutely vital that we identify the root causes of disasters. You might think about tornadoes don't always just cause the disaster. It's all these other issues that we're thinking about over there, population growth, building code adoption, and so forth, that really affects when hazards become disasters. So our field demands this kind of convergent research. And also, I'd be happy to share this with any of you. This is our recently accepted and forthcoming paper in a special issue focused on the NHERI facilities. And we offer for the first time a definition drawing on 20 years of convergence research, a definition specific to our field. So let me know if you'd like a copy of that. third reason that we're promoting convergence research is because I would argue there is not only a scientific rationale for doing this kind of work, there's also an economic and moral urgency to this work. And Joanne, I just crossed my 15-minute mark, so know that I'm wrapping up now. So last couple of things I want to share with everybody on the call is the other two major tasks of Converge are to connect researchers to various resources. And so we'd really like to know if you plan to apply for a rapid grant, a career grant, one of these convergent research awards, because we'd like to connect you to this broader ecosystem of the NSF-funded extreme events research and reconnaissance networks, as well as to the NHERI facilities that are specifically supporting this extreme events research. And we meet every single month so we can try to advance this agenda. We also have other things I wanted to share with you, like if you're an engineer on the call and you're hoping to partner with a social scientist on one of your grants, we have several pages on our Converge website that help you to know what the different social sciences are and thus who might be the best partner for what it is that you're doing. If you're looking at culture, you might want to work with an anthropologist. If you're looking at historical drivers of disaster, you might want to partner with a historian. And so we have that all up on our website. We also have our fifth and final thing I wanted to share with you today is we also fund convergence research and implementation in the form of smaller quick response grants that support convergent teams. And we also just funded 90 convergent oriented COVID-19 working groups that are bringing together researchers across 3 or more disciplines to advance the work. And so with that, my time is up. I thank you all for listening. I can't wait to read your responses to the questions and to share them with the broader Converge Leadership Corps. For now, as Karina asked, you can find much more information on our websites that are up there. On there, you can sign up for free resources. My email is on the page. And last two things, I had wanted to put a plug in for our upcoming natural hazards workshop and our researchers meeting. We just confirmed on Friday that Kelvin Drogemeyer, who is the acting director of the National Science Foundation and is the chief science officer in the Office of Science and Technology Policy for our nation, is going to be our keynote speaker here, as we hope you'll join us, and we hope you'll join us for the workshop. Thank you for listening.
We did have a question about the certification, Lori. If you can tell us how long that will take.
Oh, yes, that is a great question. So right now, and thank you for the question. So right now we have 4 training modules that are currently available on the Converge website focused on social vulnerability in disasters, disaster mental health, cultural competence in disasters, and then the one we just released is on institutional review board procedures if you're planning to do research with human subjects. And so right now we just have individual certificates for each one of them, but our 5-year plan with Converge is to roll out enough of these modules that we can actually have a credentialing system. And so we're probably 2 years away from a full credentialing system, and it's going to take our partnerships with the other engineering-led ERs to make that happen. But for right now, the individual certificates are available for every single one. Thank you for the question.
Thank you, Lori. And if anyone else wants to post some questions, you could do so in the chat box for Oregon State University, for the wave basin and the wave flume, and as well as for the CGM, the Center for Geotechnical Modeling. Another question that was asked, and this was from one of our registrants, was, Lori, there was the question about the database for Converge, about whether that would be, when that would be completed.
You know, and I saw that question, and thank you for the question. I wasn't quite clear on what that meant, what database that was referring to. We definitely have a large, we have a very large 1,100 member database for the Social Science Extreme Events Research Network that is live on the Converge website, and where you can search for social scientists by expertise and by location. But then I wasn't sure what database that was referring to.
Okay. Yeah, it wasn't clear which one they referenced, but maybe if someone's on the call that asked that question, maybe that could be a clarifying point. There's another question, and this is for any of the labs. How has COVID-19 limited access to the labs, if at all?
Thank you, Karina. I may ask for our particular case. We've been closed since the end of March. We only were able to perform critical activities, but since last week we are coming back, and we are now well, returning to normal operation. It is going to take a little bit of time to really be in full operation, but we have resumed activities since last week. And if everything goes fine, we will just keep ramping up and be as normal as possible. Yeah.
Thank you, Pedro.
Yeah, it's the same thing at UC Davis. We have been doing critical research, and we still haven't ramped up our research like literally, like just Pedro mentioned. But I guess we are looking forward to increase our research and get more researchers. Right now, we are like practicing 2 researchers at a time, and we are following all those 6 feet rules and 280 square feet for researchers. So that's how we hope that we can start full operation soon.
Thank you, Samit.
And ours is, we're obviously not a large facility like the ones you've heard about this morning, and so Converge is very different. Much of our work is desk work, so to speak. But then one of the big ways that we have been impacted is obviously through the Extreme Events Reconnaissance and Research Network, that so many of the field teams that would be going out to do post-disaster damage investigations or to do field research are not able to do that work. And so one of the things we're doing through those COVID-19 working groups that we funded is that several of the working groups we funded are actually focused on methods and ethics and how this pandemic is reshaping our approaches to doing social science and interdisciplinary research. And so I guess the thing I'd say is just this is upended everything. Obviously, I saw today just the death toll is dramatic, and just really want to acknowledge that. And we're trying to do everything we can to learn from this research community about how they're adjusting and adapting in response to it. So that's a great question. Thank you.
Thank you. There's another question for OSU. Do you do peer scour tests for multi-hazard storm events?
Sorry, can you say it again? It's cracking up.
Do you do peer scour tests for multi-hazard storm events?
I'm not completely sure the details of that, but yeah, we have done experiments with geotechnical foundations. It is possible to do scouring, and for example, we haven't shown the details of some of the experiments that we have done, but yes, what we call mobile bed studies is something that we have done in the past, and is again, it's a matter of reorganizing and preparing the facility for that. It is possible. We have done testing with sand, and also we are now working with the possibility of adding muddy waters. Yeah.
Thank you, Pedro. And this will be the last question. It's for Converge. Do you help build up research teams for a certain proposal?
So, will you say that again, Karina?
The question was, do you perhaps help build up a research team for a certain proposal? Is that something that Converge can do?
That is a great question. And so we do not specifically sort of mix and match for proposals, but that's one of our upcoming Converge training modules, is how to build, drawing on the science of team science, which really undergirds a lot of the work we do at Converge. Is we're doing a training module that is focused on that, how you can build the most effective functionally diverse as well as demographically diverse teams, because there's this whole body of research out there that shows when teams are functionally as well as demographically diverse that they oftentimes perform better. And so that is one of our forthcoming training modules. So that's one way. And then the second way is through getting involved in those EERs. We have learned a lot from STEER, for example, and from GEAR, and then sometimes they will say, we'd like, is there a social scientist who is available to go on this team? And so we haven't yet quite got to that next level where we've been able to fully do that kind of meshing, but those are definitely conversations we've had through the leadership core and so forth, so we're sort of the next step ahead with that.
Great, thank you. That's great information. And so I want to thank Pedro and Samit and Lori for your presentations. Thank you for providing this information.
Thanks, Joanne and everyone. I'm happy to be here to talk to you a bit about DesignSafe, the cyber infrastructure component of NHERI. My name is Ellen Rathje, and I'm a professor here in civil engineering at the University of Texas at Austin, and the PI for DesignSafe. So first of all, let me start off with what is DesignSafe. It is a web-based research platform that provides researchers a breadth of tools that they can use in their research to manage, analyze, understand, create critical data for natural hazards research. So I know many of us, including myself, may not spend a lot of time in the lab, but you analyze a lot of interesting data. You may do computational simulation, and so DesignSafe is here not only for the experimental researchers, but those of you who do not do experimental work. So our vision for DesignSafe is not simply to be a data repository, but to be a cyber infrastructure that becomes part of the research discovery process. To reach that vision, there are really three main components. We do provide that platform for data sharing and publishing. We work to enable your research workflows and give you expedited access to high performance computing. And we deliver cloud-based tools that support you in the work that you do to analyze, visualize, or integrate diverse data types. And through these components, hopefully we can amplify and link the capabilities of natural hazard researchers in the US and also abroad, and across the experimental to simulation to field research communities, and really bring them together, and also to expand beyond engineering. Lori Peek always reminds me that how important it is to bring the social scientists into our purview to really understand natural hazards. So we have that goal as well. So if you go to our website on designsafe-ci.org, you'll see that we represent the entire NHERI community, so the NHERI facilities. You can find information here. There's information about the general NHERI community, learning center, etc. But the part that represents the DesignSafe component that enables your research is here, the research workbench, where we have access to the data depot, our workspace, the reconnaissance portal. You also see a link here to the SimCenter research tools that Laura will talk about in a bit, and then also the user guides. So if we take a closer look at the workbench, first, importantly, we have the data depot data repository, and there are different levels of access and different parts of the data depot that you might find useful in your work. There's the private space, which is yours alone. It's called My Data, and you can put files there that you're working on. When you move on to want to collaborate, we have a project space. So that collaboration space under My Projects, where you can share files with a group, and then ultimately publish those files. And not all of those files necessarily. It could just be a subset of what you ultimately want to publish. Once those data are published, then it goes into the publicly accessible published area where our curated projects reside. And then finally, one other place is community data, which is also publicly accessible, but is uncurated. So that may be a place where you just want to put some files up to make them available, but you don't want to go through the full curation process. So moving on to the tools those can be found in the Discovery workspace, the apps and tools that enable computational simulation, data analysis, visualization, and all those tools have access to the files in the data depot. And then finally, the reconnaissance portal, where it's a mechanism to discover published reconnaissance data from natural hazard events. That data may ultimately reside in the data depot, but this is an easy way to parse it and find out, say, what different data sets are available for a specific event. So let's talk a little bit about each of these in a little bit more detail. Here in the data depot, I'm logged in as myself. You can see the My Data section, the projects, the published area. These are projects that I have access to. Some of them I'm a PI, some of them I am not. But a key is it's a space to share data, files, results with your collaborators and eventually publish those data for public use. Of course, you may decide nothing is publishable from the work and you may not publish it, but we still have a mechanism here for you to share with your collaborators. Should also mention you can link to your other cloud service providers you may have accounts with, Box, Dropbox, and Google Drive. And that'll easily allow you to interface with those other cloud service providers. And then of course there's the published area. So if I were to publish data from one of these projects, you might see something like this. Here's an example from the centrifuge at UC Davis. Scott Brandenburg as the PI, so doing some soil foundation structure interaction effects. And you can see here we've got something that looks like a publication. There's actually an abstract. There's some description of the experiment. And then ultimately, as you scroll down, we can see the data organized within having some reports, describing the model, the sensors, and then ultimately the data. And then importantly, that data has a title and a DOI so that when it's used, this data can be cited very easily in a journal paper. I want to encourage everyone who is doing research in natural hazards engineering to publish your data and then cite your data with a DOI. It really helps the entire community with reproducible research, building new research on published research by having that data ultimately available and citable in your paper. So moving on to the workspace here, we've got a plethora of cloud-based tools and codes that take advantage of the HPC resources at TAC, the Texas Advanced Computing Center, such as Stampede 2, and the more recent addition of Frontera. And so you can see the tools are split between simulation, visualization, data processing. We have some links to partner data apps. And then there's some utilities that in fact we can work with you to create your own apps. Currently the HPC enabled codes that are available in the web-based workspace are OpenSeas, LS-DYNA, which is a commercial code, but we have a bring your own license agreement with LSTC. So if you have a license in your academic department, we can give you access. For storm surge, we've got AdCirc and SWAN. For computational fluid dynamics, we have OpenFOAM and more coming. I should note that the codes here that are available in the workspace are also available from the command line. They do require you to get an HPC allocation with TAC, but it goes through Design Safe. It's an expedited review process. And we can get you access, obviously, to the traditional CPUs that are generally used by many of these codes. But if you're also interested in using GPUs, say for some AI applications, we'd be very happy to work with you. If you can send me an email, send a ticket about ideas on how you want to use Design Safe. The website is really just the starting point. We have a lot more capabilities we can help you with. And over our next 5 years, we're really looking to build up on the AI work that's being done using Design Safe, so we'd be particularly interested to talk with you. Looking at the workspace, some of the cloud-based tools for data analysis, we have MATLAB, which I think we've all been using for decades to do data analysis plots. We have some batch processing available to use it on the supercomputers. But we're also trying to really emphasize Jupyter because it's open source, first of all. So MATLAB, if you're at an academic institution, we can give you access easily. But Jupyter is available to everyone. That electronic notebook, you can run Python analyses, you can run R analyses. Again, files in the data depot, you can have access to the supercomputers, etc. If we move on to visualization, and here visualization really has some significant potential because if you're trying to visualize large data sets, you can't really email them to each other. So the idea is bringing the tools to the data in the cloud. Keep the data in the cloud and have the tools there as well. We have a tool called HazMapper, which is kind of our version of Google Maps. Doesn't quite do as much as Google Maps, but allows you to bring in reconnaissance data and other geospatial data and share it with your colleagues. ParaView and Visit for various types of scientific visualization. Potri, which you might hear about from Lara when she talks about the Rapid, because they're collecting a lot of point cloud data, and Potri allows you to create, view, and analyze that data. We have the open source QGIS for your GIS applications, and then some other AdCirc specific tools such as Kalpana and FigureGen for data conversions and plot generations. Just to give you an idea of what Jupyter can do, because we're really looking to expand the capabilities of Jupyter again over our next 5 years. You'll see we've used it as an electronic notebook where you have some rich text, equations, but it's also got codes. It even have tools where you can click on a sensor and actually view data and maybe clip data and then export it. You know, having the drawing right there that shows you where those sensors are. So lots that you can do in electronic notebooks. We took some of the work that we had done in the late 2008, 2009 framework on probabilistic assessments, created a Jupyter notebook, published it in Design Safe here. You can see about 2.5 years ago. You could put a latitude and longitude in. This uses the USGS API to pull in ground motion hazard, earthquake ground motion hazard information to develop probabilistic assessments of, in this case, slope displacements. But it really is versatile in terms of what you can do in Jupyter. Moving on to the reconnaissance portal, as I mentioned, you can identify archive data sets from reconnaissance events. We've had a lot of natural hazards that have occurred around the globe, lots of hurricanes. You can look at the map and click on a map point. You can search the listing on the left as well. But just to give you an example, if you click down here in New Zealand in 2016, they had the Kaikoura earthquake, and Joe Wortman and I led a gear reconnaissance team there. And part of that work, we developed a landside inventory. So here you can see for the event, we zoom in. These are the available data sets. Some are in Design Safe, some are external. And in this case, the earthquake landside inventory was published here in October 2017. You can see a GeoJSON of the data set, which can be opened in HazMapper, which is available in the workspace. And here you see the landside inventory, some photographs, our GPS track logs from some of our aerial reconnaissance, as well as ground-based reconnaissance. So I'm just going to finish off with a couple of slides here. The Learning Center is where there's links to education and training, not just for Design Safe, but really the broader NHERI community. You can see we've got Design Safe tutorials, we've got Sim Center webinars. We host those. They're also available on our YouTube site. So we have a YouTube channel where the webinars are archived. We have user guides specific to Design Safe within the user guide link here. And there are tooltips on every screen for trying to give you that information you need when you need it in terms of using Design Safe. So Design Safe takeaways, I think number one, we're here to help you achieve your research goals. We are available for all natural hazards research, engineering, risk assessment, social science, societal effects. We are here for you. If what you need is not here, tell us. We can work with you. Contact us. I mentioned at the beginning of my talk that Tim Cockerell slacked me to tell me, ooh, they might need you ASAP. Well, Slack is we have a Design Safe Slack team that you can join. You should get an invitation when you register for a Design Safe account, but if you don't, you can go into NHERI community, go to the Slack online collaboration and request access. And you can interact with other Design Safe users, look at different channels where people are communicating and posting messages. And one thing that we ask is if you do use Design Safe and make use of Design Safe to do some research and publish ultimately a paper, we would love it for you to cite what we call our marker paper, which we published in Natural Hazards Review in 2017. And so you see that here and also linked on the website as well. So the contacts for whom to contact are shown there. Myself as PI, as well as Tim Cockrell, my deputy director, is also the director of user services at TAC. Oh, and here's just an example of what the Slack area looks like. For instance, here in Jupyter, if you're having Jupyter problems, you can say, hey, is there any support for running Jupyter Notebook? And we can answer, we can get together and start a one-on-one conversation. So.
The RAPID facility is a unique facility that first of its kind that was established as part of this process and provides equipment and resources and support and training to do field reconnaissance projects. The team is quite broad, includes specialists in earthquake engineering, wind engineering, geotechnical engineering, coastal engineering, social science, etc. And we've got 3 full-time staff people that you see on the right here who can provide expertise on identifying appropriate equipment, help you get your field reconnaissance effort up and running, and then also can go into the field with you in particular occasions if you need additional staff help. The facility is located at the University of Washington in Seattle, but includes people from across the country. The primary mission of the facility is to provide investigators with the equipment, software, and support services needed to collect, process, and analyze perishable data from natural hazard events. We promote reconnaissance-based science, shared resources, open data, interdisciplinary research, community engagement, and innovation to reduce the impact of natural hazards. Specifically, we've spent a lot of time and continue to spend time acquiring, maintaining, and operating state-of-the-art data collection equipment. So that means keeping apprised of what's developing in the community and identifying that equipment, which is going to be most useful for people who want to do field reconnaissance, acquiring it, figuring out exactly how it works, putting together guidance on how to use it. We are and continue to develop the RAP, which is an application that runs on an iPad or an iPhone soon and allows you to do everything with respect to your field reconnaissance, from setting it up, downloading manuals, coming up with a reconnaissance plan, viewing data, collecting field notes, audio, et cetera in the field, automatically uploading that so it's archived, and then also providing surveys, so you can build a survey and do surveys in the field. Those could be interviewing people, or they could be collecting information about a particular site. We have a substantial training effort so that people know how to use the equipment and have a better understanding of field reconnaissance, and then provide advisory service and basic logistics. So if you're interested in doing field work, first thing you want to do at some point as you're planning, talk to our staff so that we can provide some guidance on what equipment might be best, issues associated with logistics that you might need to understand. We also facilitate systematic archiving on Design Safe and do some community outreach and education as well. In the old days, when you went into the field, and I certainly am old enough to remember this, because really it wasn't that long ago, we took tape measures and cameras that had cards in them, and we went in and we got a few measurements around a site and a whole bunch of pictures that were really hard to figure out exactly what you were taking pictures of when you came back. And so this shows some pictures of the old days of field reconnaissance. Now we go into the field with drone-based LiDAR drone-based cameras that can produce 3D point clouds with photo overlay, which is what you're looking at. And we can go back to the office and we can say, oh, you know, I want a measurement right here of what's happening on this little, right here where it's settling. How much, what's the settlement there? What's the settlement over there? How big is that crack? You can go back over and over and over again and interrogate this 3D point cloud so that you can really get all the information you want out of it. We take large amounts of this kind of 3D point cloud data, lots of digital 2D images, and then lots of field notes and surveys, etc. This kind of, this slide shows somebody in the office in a cave. So you've got this 3D image and interrogating that 3D image to pull out information. This slide is the most depth that I'm going to provide on all of our different equipment. And you see at the bottom is our website. I really suggest that you go there and take a look at what's available. We have 5 terrestrial LiDAR units that can provide up to sub-millimeter resolution. It takes a long time for that, a couple hours if you want to get the full 3D in sub-millimeter, but it is absolutely amazing. And we just took it to Japan and we can actually identify cracks in concrete. We've got 7 drones that many of which you can train on and use yourself. One that needs to be used, that requires our technicians to use. Some of them have LiDAR, all of them have cameras so that you can take pictures that then become a 3D point cloud via structure for motion. We've got a boat, I forget the name of the boat, that collects bathymetry so that you can get the surface, underwater surface. We've got pressure gauges. Down here in the left corner, we've got total stations, so you can locate a point in the world via GPS and then connect your LiDAR to that point so you know exactly where you are in the world. We've got seismographic arrays and shear wave velocity profiling. We also have some new wireless accelerometers that you could put on a building. We've got our own street view that you can layer on top of SFM data. And then we've got our RAP that I was talking about, which just is the tool that you're going to want to take into the field to both collect data and then go back to things like what does this red button on this piece of equipment mean? And then make sure that everything gets archived. Helps you plan your activities for the following day. I thought I would spend most of the time that I have talking or showing you some recent field studies and just giving you an idea of what you can do with rapid equipment. Here's a long list of them. They include earthquakes, hurricane damage, wildfires, slope failures, etc. This is one particular mission that was a GEAR-sponsored mission that went to Indonesia to map a flow slide using drones. At this bottom picture here, the black and white target is showing you a target that they located in space, so they get the GPS coordinates of that very accurately using the surveying equipment. Then you send up your drone, take a picture of that. Now all of your drone-based images are connected to that point, so you know exactly where they are. This is showing you a satellite image of the flow slide and the image that was collected using drones with cameras and then Pix4D to generate the point cloud using structure for motion technology. You can see it's a phenomenal image of what's happened. That's now your image, and you can go in and you can go through and get millimeter resolution on what some of the cracking is, what the flow looks like, what the buildings are, where the buildings are, etc. So just amazing amount of data that you can use. This shows you the 2D or the 3D layout of the flow slide and the surface, and then some of the information that was pulled from that and put into this journal publication. So on the right here, you can see the orange line, which is showing the post-earthquake elevation, the blue and the green that were showing the pre-earthquake elevation. You can see how the slope is slid and filled in some of the lower areas. Here's some images that are coming from STEER or a project that went along with STEER after Hurricane Michael. It was looking at large volume buildings. PI was from Auburn University, and the need for going in and looking at these high volume buildings was established based on preliminary recon work by SEER teams. These are, again, 3D point clouds that were developed using terrestrial LiDAR. And you can see up on the top that it's kind of hard to see some of the actual structural system, but then using some of the software, you can pull away the debris and the non-structural mask and get down more and see the structure better. This shows some images that were pulled, or some point cloud, portion of the point cloud that were pulled out of the whole system. You can see some of the trusses that failed due to uplift from the hurricane force winds that came into these large volume buildings, and then rather than pushing down, per gravity load pushed up, and this caused these truss systems to fail. Just another image that was then interrogated back in the lab after the recon effort, and this was obviously collected using drone-based cameras. Our equipment can also go to some of the NHERI experimental facilities. Admittedly, this is our equipment at the Miki shake table in Japan, being used to collect information about a couple of buildings that were tested on the shake table there. This shows you the 3D point cloud, and as I said, we went recently and used this equipment or similar equipment on some tests of concrete structures, and we actually were using newer equipment than this, and we're able to pick up sub-millimeter resolution and visualize where these cracks are in some of the concrete structures. Similarly, this has been used at the UCSD facility to monitor the response of a cross-laminated timber frame that was tested there. If you are the least bit interested in field reconnaissance work and using our equipment, I would recommend that you partake of some of our training. We have a 4-day intensive training workshop that we've held annually during the summer. It was postponed this summer, and we're looking to hold it in January in Gainesville, Florida. Provides extensive hands-on training. You get to use all the equipment. You get to look at processing some of the point cloud data. Highly recommended if you want to take the equipment into the field. We also do 2-day joint training workshops with other NHERI equipment facilities. Gives you a better understanding of the equipment, but not the hands-on. We recently did a 2-day data processing workshop at the UW Rapid facility. We've only done one of these so far, but we expect to do more. And then there's also ad hoc training. If you're going to take equipment into the field, you've done the 4-day event, you want to brush up, you haven't done the 4-day event, you just want to understand, make sure that you can get a little bit more work with it before you take it out and ask the questions ahead of time, we can do ad hoc training at our facility as well. It's open to anyone. The Rapid facility equipment are available to all. Priority is given to NSF grants and for natural hazard reconnaissance, but it can be deployed for anything. I go to the website. All the information about pricing, equipment, et cetera, is on the website. And that is the end of my Rapid presentation. Hopefully we'll have a minute or two for questions at the end. So the Rapid facility allows you to collect large data sets in the field. They get uploaded to Design Safe for archiving and some post-processing. And then eventually, my personal goal is that those post-event data become data that validate regional loss assessments and simulations for regional loss, regional damage using SimCenter resources. The NHERI SimCenter facility is, again, a large team of people. It shows the management team, the development team, and domain experts who provide input. It's located at UC Berkeley. Obviously, it's in the cloud, but most of the management team is at Berkeley, Stanford, University of Washington, and Notre Dame. The intent is to provide a framework that enables researchers to investigate regional loss. And I'm a structural engineer and earthquake engineer, so this is my regional loss estimation. It would start with simulating the earthquake event across a region,
looking at site-specific ground motions, using those site-specific ground motions as input into a suite of building models, taking the building response, putting those into loss and regional risk assessment models, and ultimately being able to characterize the impact of this earthquake on the Puget Sound region, since I live in the Puget Sound region. Obviously, this can extend to a hurricane simulation or other hazard simulations, but that's ultimately the goal. And layering upon that, we want to leverage the high performance computing capabilities that are available via Design Safe. We want to add uncertainty quantification, and we want to make it so that it's possible to swap in and out new software and data sets. So you may have a particular FEM or a particular piece of software you want to use for your site-specific ground motion. You should be able to use that. We're going to seed it for you, but you should be able to use whatever you want. And now, as technology advances, we're looking at adding tools that enable you to generate the required data sets using AI, perhaps to create a regional BIM from city records. I need to know what the built environment looks like. And so there need to be tools to do that. And then obviously we want to be able to look at multiple natural hazards, possibly simultaneously if we're thinking about wind and storm surge. We get a lot of questions about how the Sim Center and how Design Safe are linked. And the Sim Center produces a variety of simulation tools. Our whale that you can kind of see grayed there is the tool that does the regional loss estimation, but there are a bunch of tools that are part of that process. Those reside on your desktop. You can start a job on your desktop, and then via the Agave interface, that tool launches simulations that use Design Safe high performance computing resources, and the data are then available on Design Safe. And so that's the link between the Sim Center and Design Safe, is the Sim Center is producing the software that is going to utilize the Design Safe computing resources. When we talk about an application framework, the idea is that the Sim Center is putting together the yellow and the red here. So there may be a software platform, OpenSeas as a finite element software. We're providing a preprocessor and a post-processor that allow you to link that together with maybe the ground motions that are coming in and some software on the back end that tells you what the losses are if the building has seen drifts of 3% in an earthquake. This goes through that regional loss estimation that I was talking about, where the full regional loss estimation would be to describe the region, describe the hazard. For each point within your region and sample of your hazard, there's an asset that you would describe, a building maybe. What happens at that particular building due to the ground motion? How does that building respond? What's the damage of that building? So this kind of shows where all these different pieces of Sim Center software fit into that. So there's WEUQ, which is wind uncertainty quantification. There's EE, earthquake uncertainty quantification. There's a CWE tool that does more on the computational fluid dynamics side. At the heart of the uncertainty quantification is QuoFem, and then the PBE tool is sort of wrapping around that, taking the results of a building simulation and figuring out what the actual damage and losses are. And then RWhale is the piece of software that just pulls all of that together. All of this then runs on Design Safe. You can run it locally. Most of what you want to do is obviously at the region level going to be at Design Safe. And so RWhale is allowing that linkage back to Design Safe. These couple of slides here provide some more detail about some of the pieces of software. So QuoFem provides uncertainty quantification for the finite element method. It combines finite element applications with uncertainty quantifications. There are 2 or 3 or 4 different capabilities. I think the ones that are probably most interesting are the forward problem, where you are given some uncertain parameters in your model. What's the impact of that uncertainty, or what is the uncertainty of your results? Or the inverse problem of using this as a way to do parameter estimation. You've got a data set, you've got a model, you can use this tool to do parameter estimation to improve your model for fitting the data. You can also do reliability analysis and global sensitivity analysis. So if I'm thinking about how I might use this in my research, I could use this for doing some uncertainty of the response of an experimental test, or taking data from my experimental tests and improving my models. The QuoFem is the basis for WEUQ, which is wind engineering with uncertainty quantification. This allows you to do some stochastic wind loading of a structure to take results of a database of computational fluid dynamics solutions. CFD is really computationally intensive, so we archive the solutions. That gives you a way of estimating the building response. This can also be a driver to a true CFD model, and then it layers the uncertainty quantification on top of it. So research opportunities, do some simulation-based design of a test specimen you're going to test in the wind tunnel or the wall of wind, or use uncertainty quantification to inform the design of the experimental test program. What parameters in your model are most critical to determining the response of the structure, or which ones are most uncertain and have the greatest impact on response? It's an excellent way to start your experimental test program. The EEUQ is similar. Instead of wind loading, we're now talking earthquake loading. At the bottom left here, you're showing a distribution of response quantities from uncertainty that's been introduced into a simulation. So maybe I don't know exactly what the strain capacity of my reinforcing steel is in my response model. At what strain does it buckle? I can make that an uncertain parameter and see what that uncertainty does to the deformation capacity of my structure. Again, really nice tool for doing some simulation design of a test specimen, maybe on the shake table, or uncertainty quantification to better inform which parameters you should be testing. The PDE tool layers the, on top of WEUQ or EEUQ, layers the impact of nonlinear structural response onto, in terms of, or what's the impact of the simulated response in terms of loss and damage to the structure. And so this is showing on the right here a cloud of loss points for a particular structure based on all of the different components that can be damaged during the earthquake loading. Research opportunity, adding additional data to this to improve our estimation of damage and loss modeling. And then finally, RWhale, that's linking all of this together for a regional simulation. Some of the RWhale exists. Some of the things that I think are really exciting about new developments with respect to these regional loss estimations are some tools that we've been working on recently, Brails, that uses AI to develop a representation of all of the structures in a region. Obviously, if you're going to do a regional simulation, one of the really challenging things these days is actually figuring out how to characterize all the built environment in your region. And so Brails helps with that using information and AI with either machine learning or deep learning to enhance your characterization of the built environment. Pelican is another tool, and Pelican at this point is combining information in HAZUS and FEMA P58 that characterize the damage and loss of a structure given, in this case on the right here, I'm showing story drift. And so it could be, what is the response quantity that's coming out of the structure, and therefore what's the loss, what's the damage, what's the time required to rebuild, repair, etc. Another one that's new is some EQSS, which gives you a regional seismic hazard mapping. And so all these little dots are what the expected ground motion record, or you've got an expected ground motion record at each of those points. So it's a prototype for scenario-based regional loss estimation. It's one way of seeding all of the ground motions in a region. And then finally, there's a new tool that's being developed that can help you, again, build out characterization of your built environment. And so this tool scrapes tax assessor websites to get information about structures and then gives you a simplified characterization of that structure for your regional simulation. Finally, I'll just show you one of our regional simulation test beds. So the idea is that you can take this test bed. We've put it together with a choice of building inventory and simulation models and a particular level of detail. You can add in, you can pull things out, you can add something new in to suit your needs. We've got 3 earthquake ones and then 1 hurricane test bed that we're working on at this point. This is looking at the Anchorage test bed. There are 2 different RWEL configurations, one that's using recorded ground motion and one that's using simulated ground motion on this grid that's shown on the right. And then these are the estimated losses based on those different ground motion distributions. And you can see that they're pretty similar in terms of repair costs, many more red tags when you're using the recorded ground motion than in the simulated, and loss ratios are pretty similar. So this would be an excellent place if you want to start playing around with how your model or loss estimation tool or whatever changes the results of this test bed. Here's some other research opportunities. As a structural engineer, like who does simulations of buildings, my question is, well, what happens if I can give you a slightly better model of a building? That's got to help, right? But there's also opportunities to validate using reconnaissance data or investigate the impact of various retrofit measures on the impact of the earthquake in the region. Lots and lots of opportunities with these test beds. Finally, we have some educational tools. As you're putting together your career proposal or like, you may want to think about what the educational component is, and these SimCenter educational tools might be a really nice avenue for expanding out your educational program. So the idea is that these are simulation-based tools that somebody can take into a classroom and use as part of their probably senior or maybe master's level classes to help students to understand the impact and the potential of simulation. There's one that is just a nonlinear multi-degree freedom oscillator up on the top left. There's a pile group tool that allows you to put in different layers of soils and different kinds of pile groups up on the right. It shows you what the deformation or the demands on the individual piles are. On the bottom left, there's earthquake versus wind, which I think is really cool. You take a building, you subject that building to both an earthquake load and a simulated wind load, and you can see how the building responds in those 2 different loading scenarios. Really helps to emphasize why you might not want significant nonlinear action under wind loading. And then on the right is a tool that was developed more recently, which is looking at simulating a buckling of a brace frame member. And it's a really nice opportunity to see how adding resolution to the nonlinear model improves characterization of the response of the structure. But from your perspective as an educator, I would highly recommend pulling these into your classroom. There are, on some of the tools, there are notes that you can present to your students and questions, et cetera. It's also a nice idea in terms of the educational component on a proposal. How to get started. Obviously, everything is accessible from the web page. We also are in the middle of summer boot camp, and we hold those every summer, summer programming boot camp, which is in C++, as well as tool training for students and faculty. And then all of that information is available on the website and online, so you can pick it up and use it to get your students started or get you started. And then obviously contacting SimCenter staff to discuss potential proposal and how you can build on the tools that we have. With that, I will say now we are open to questions.
So we have a few questions that have come in. I'll do the first that was shared in the chat box for everyone. And this is for rapid. How likely would it be in the future that rapid research may provide intensity and damage distributions for all major natural hazard events within the US as well as around the world?
So the RAPIDS charge is to provide the tools that researchers need to go into the field and collect the kind of data that might characterize that. So the RAPID would not do that, but the RAPID would enable you all, all of us to do that. And I think as one could envision that as the tools develop and the software develops, it will be easier and easier to do that more quickly. There are also surveys that are part of the RAP. So when a steer team or another team goes into the field, they're using a consistent survey. And so then it's very easy to take all of that survey data and rapidly present it.
Let me just follow up on Laura's answer. This is Ellen. I think when we look at Converge, which I think Lori talked a bit about earlier today, these extreme events reconnaissance organizations really have the charge to try and do that type of work. And the tools that the RAPID is developing will assist in that work. Design Safe provides the opportunity to publish that work so that you can use it. So I think that's how it all fits together.
So there's another question about TAC and Design Safe. What is TAC and its relation to Design Safe?
Great, that's a wonderful question that I didn't make clear. So TAC is the Texas Advanced Computing Center. It's a supercomputing center at the University of Texas that is funded in many different ways. There's 100+ employees that do a lot of research and support for scientific computing and analysis. All of the software development and all the hosting, the storage, etc., is done by TAC. And you see Tim, who is my deputy director, put in the chat the URL for the TAC website, so you can learn about all the different capabilities there. So Tim, I don't know if you want to expand on that, since you actually work for TAC.
Yeah, as Ellen said, we have nearly 200 staff members at this point, full-time staff, about a third with PhDs. Who have experience spanning a lot of scientific disciplines and working in high performance computing, but also data analysis and data assimilation. And so we can help support lots of research needs with personal support, with expert staff that can help answer your questions and help direct you to the right resources. Whether we have those resources at TAC or if it's part of the network of the National Science Foundation resources for which we are a part of as well.
And I think you bring up a good point there, is that we can leverage a lot of expertise that's at TAC that may not be specifically funded for every minute of their time through Design Safe, and they work with us. I should also mention that something that we're going to be starting over the next 5 years is a Cyber Infrastructure Summer Institute. We're trying to not take the Summer Institute name from you. I think actually we called it the Summer CI Institute, where we will invite postdocs, graduate students, maybe early career faculty as well, to do an extended in-residence time in the summer here in Austin to work. We'll have like a week-long set of activities for people to interact with the TAC staff, maybe work on some of their research directly with the TAC staff. And if you want to stick around for a month, and we'll give you a desk and you'll have those relationships and really start to dig in deep with some of the technical folks at TAC.
Thank you, Ellen. And actually there was a question about what may be modified or added in the next 5 years. And so this is a program that you're considering, but are there other other things, and this also could be for Laura, that you may be adding or modifying in the next 5 years?
Yeah, I'll start first. So as I mentioned, AI and machine learning, we have capabilities, scikit-learn is available via Jupyter and Python. So you could do it today, but we really want to expand on that. We want to expand on the ability to use GPUs for some of the neural network type work, deep learning work. We're always enhancing the data repository. We want to add data versioning. We want to add some better ways that metadata can be scraped so you can find things a little bit better. Really pushing Jupyter as a workflow engine so that you could do your pre-processing, shoot your jobs off to the high performance computing system, then do your post-processing, things like that. So we've really just scratched the surface on what we can do. So what we're looking, we have these ideas that we're going to be moving forward with, but we're always looking for new ideas and new ways people want to use Design Safe, because we're trying to be as nimble, as flexible as possible to really take advantage of the experiences we hear about from the community.
I'll just add that for RAP, we are sort of in the process of brainstorming about what other things we want to add. One thing that we're really excited about right now is this RAP and continuing to develop it out, because it is so valuable when you're in the field. And we see these RAP surveys, which are questions that you can set up ahead of time for your team, as being really important across all of the fields. So they started out as support for the social scientists, because that's the type of information that social scientists are often collecting, is an interview with an individual who's affected by an event. But now we're seeing it also as a tool where you can do some of the questioning that STEER does, in terms of here's 10 basic things you need to describe about the structure. You can envision that expanding out to a lot of these different areas. And so that just becomes a very nice tool. And then working with Design Safe on how to visualize this geolocated data and make it easier to bring make it easier for people to do the post-event evaluation of the data and assimilate all of that data into a meaningful story about what happened.
I have one more question, but that people have submitted. But if you have other questions, please make sure and post them in the chat box. The next question, and I guess this, if there's anybody else too from the experimental sites, how would participants from a research group and the host facility interact and share credit for the experiment? And in this case, also with data.
Well, I might be able to start, since there's a whole bunch of sites and maybe we don't want them all to chime in. But what we've seen is many of the sites will work with you to design the experiment, and they may be co-authors on the data publication. Certainly the experimental facility is shown as getting credit for having generated that data. Other cases, the staff at the experimental facility may say, this is our service to you. You guys are the authors of the data set, because we help you generate it, but you're the ones who analyze it, process it. So it really probably goes facility by facility on how they want to deal with the authorship on the data publications. But you can have a long list of authors on a data publication the same way you can have a long list of authors in a regular paper.
For the RAPID facility, it's been, unless there are RAPID staff who are really actively engaged in writing the proposal and doing the data analysis, the RAPID facility provides a service of helping you to collect the data, helping you to identify the right equipment to take, and helping you to use it in the field. And it's your data, and you publish it.
Thank you both. There's a question about the RAPID equipment. Can that be used for hazards other than earthquake, surge, or wind, such as riverine flooding?
Yes, we've had a wide variety. We've also used it for wildfires. There's some prioritization in terms of both what entities can use it and then what disasters come first, but it can be used for anything by anybody.
Okay, thank you. There is another question, just real quickly. The priority list for use of RAPID equipment, is that something that's available online?
Yes, it is.
So before we begin, I want to remind our participants, those of you that are logged into this call, thank you again for being with us, for for a long day, but I guarantee that this panel will be worth it. In our regular Summer Institute, this is one of the events that gets some of the highest praise in terms of the advice that the panelists give to help future proposal writers in their their own planning. And so I want to encourage you to ask as many questions as you'd like. Please post them on the chat box. You can start doing so as soon as you'd like. You can send them directly to me and I will ask them, or you can also post them so everyone can see. And we're going to go through the panelists one by one and let them introduce themselves. They'll tell you a little bit more about themselves, and I have put together some slides for a slide per presenter so that you can see who they are and some more information about their award and a small piece of advice that they would give. And so if we can start with that, again, thank you to the panelists. We have 4 amazing researchers and just human beings in general that have volunteered to be part of this panel to share their experiences. And so we'll start off with Stephanie.
Hi, everyone. My name is Stephanie Paul. I am an assistant professor at Texas A&M University in the Civil and Environmental Engineering Department. The award that I got through NSF was the Career Award this year. It's about transfer learning using basically artificial intelligence, leveraging that and all of the amazing abilities that we've already accomplished in civil engineering to move a little bit of a step further. So I'm using Design Safe and the data that's on there throughout my project and have over the last 5-10 years. And then my one piece of advice was to love your idea. So basically whatever NSF project, this is the first NSF award I've received, besides I was part of a workshop before on 3D printing in civil infrastructure. But regardless of whatever you're doing, when writing a proposal, it's a lot of work. And so my advice is to really be the biggest champion of that work. That will allow you to network and meet the right people, as well as just to get your idea out there and to be challenged by people that you're talking to make sure that you're honing that idea, and so on and so on. That's all for me.
Thank you, Stephanie. Next up, Elena.
Hey, thanks. Hi, everyone. My name's Elena Sutley, and I'm a professor at the University of Kansas in Civil, Environmental, and Architectural Engineering. Similar to Stephanie, I got the NSF Career Award, and the project is on measuring the relationship between organizations and within the community and how they can facilitate and enhance disaster resilience and recovery. And so with that facility, or with that project, I'm using 3 different NHERI facilities, including the Sim Center, Design Safe, and Converge. And so then some advice, really, I think this is specific. Yeah, this is definitely specific advice to the Career Award, whereas like I love Stephanie's advice, being great advice always. And so that's, while it's generally natural to see how your research plan will feed into your education plan, it's critical to get that feedback loop of your education plan back into your research. Just noting that that integration goes both directions. And then to propose a project with concrete outcomes during and after the 5 years. So you need to have a project that you're doing that's clear in your proposal, but it also has to be clear how that's gonna, how your work is in your career is gonna build on that well beyond the 5 years. So it needs to be very obvious too how you're gonna keep extending that work beyond that single project. So anyways, excited to talk to you all today.
Thank you, Elena. Next, Arindam.
Oh, hi. Thanks, Karina. Thank you, everyone. My name is Arindam Chaudhary. I'm the PI and director of the Wall of Wind Experimental Facility at FIU Miami. And I got my career award way back. And it was on full-scale simulation of peak wind loads to reduce hurricane damage to low buildings and use of the related research to develop hurricane engineering expertise. So my advice would be like most of us, we write so many research proposals for unsolicited. We know how to write the research part, but I think as Elena mentioned, the integration of research with education is extremely important, especially for a career proposal. And to do a good job, it's not only just important to read your research area. That's what we do, generally read the research journals, but also you have to read educational journals so to see what is the current state of the art in the education, because the pedagogy is changing at a very fast rate and new learning methods are coming up. So if you are not conversant with that, it will be very difficult to integrate the research with education. So that's would be my advice, that as you read research papers, also read educational papers so that you can do a seamless integration after you understand what is the lack in both the research area and the education area. That's all.
Thank you, Arindam. And our final panelist, Forrest.
Hi, everybody. It's great to be with you. This by far is one of my most favorite things to do, fun things to do during the year, because we get to meet all the assistant professors that come in. So for those of you that are kind of brand new or just getting started, welcome to the natural hazards community. Maybe you know seismic, maybe you know wind, maybe you know coastal hazards, but guess what? Now you're stuck with us. You're part of the larger community. So happy to be here with you. I've worked on a lot of different projects for different federal agencies. Here at the University of Florida, I work with over 300 faculty that are working with every group you can think of under the sun. At any point in time, we're working on 800 or 900 projects. So I spend a lot of time working with faculty, helping train them up to get them prepared. And the career is just a really important first step for many of you. This is a great opportunity to really start figuring out how you're going to, communicate in a technical and persuasive way. So hopefully today we can impart some wisdom. So Karina asked us to give us one piece of advice, and having spent lots of time with assistant professors, I'll just, and even senior professors, because this isn't really an age thing or an experience thing. It's always important to give the bottom line up front where everybody's busy. And when you're writing a proposal, you need to really lay down the framework for what you're trying to do early. And you need to get the reviewer excited and give them a clear vision for what you're trying to accomplish. And hopefully with some of the questions, we can touch on some of the elements of that later. Thanks for having me with you.
Thank you to our panelists for introducing themselves. And I again want to encourage everyone to post questions on the chat box, either privately to me or to all. But I know that this was a question that was asked last year at the Summer Institute. And for those of you who submitted the Career Award, how many times did you submit before it was successful?
Yeah, it was my second time.
It was my first time.
I'm not as lucky as Elena. It took me 2 times.
I'm the extreme case. Mine was 3rd time.
So is there a limit of 3? Is that correct?
Yes.
3 submissions. Okay.
And they've also just changed the date, so you could submit right up until you go up for get promoted to associate professor. So you got a little bit more time starting this year than you did in previous years. Not that you should wait.
So in In Elena's case, for example, did you do something to prep? Did you have like a long prep time before you submitted? Did you talk to a lot of people, potential collaborators? Like, how was that process?
Yeah, thanks, Karina. I'll just clarify with collaborators, of course, the career is a single PI award, but yes, I definitely talked with a lot of people, you know, leading up to preparing my career proposal. I'm pretty sure I probably talked to both Forrest and Arinda for that matter too, as well as Lori on this call, and there's probably others on this call that I talked to at some point in the few years before I submitted my first one. So yeah, and that was just critical for me to kind of get, you know, learning the landscape of how to write a competitive NSF proposal. That was just my biggest strategy for it, was talking to people who had been successful in getting NSF awards, including talking to the program director at NSF to make sure I understood the specifics to their program, because that's where, if you're going into the ECI program versus HDDE versus maybe a third program, there may be different things that make you your proposal more or less competitive across those programs. So I made sure that I talked to the program managers as well, so that I could understand that aspect of it too.
Thank you. Thank you, Elena. And I also want to ask the rest, for you that submitted multiple times, what did you learn after submitting that first initial time?
So I would add, you know, you need to submit when you're ready. You know, often people sit it out the first year. I think it's more common to get started in the second year. As I recall, there was a lot of pressure on me at the dean, where I was at a different university, my first university. It's a lot of pressure to apply for these, and I wasn't really ready the first time, but it was a good experience. But when I did the second time, that's a longer story, but I ended up learning a lot about myself, because I was actually down in South America. I was with my wife's family in Brazil, and I got dengue fever, and I got tremendously sick. I got stuck back in the country for about 3 extra weeks. So I got back and I had a week left to submit my career proposal. And I went to my chair and I said, well, what do I do? And he said, well, the dean's not going to be upset at you if you don't submit, or sorry, if you don't win, but she will be maybe a little upset if you don't win, if you don't try. And so it was a week long working around the clock to get it done. And, you know, I guess the lesson to maybe for both of these is that you really do have to, you know, exert yourself, and you got to just kind of throw yourself into it. Some people just wait too long because they're maybe reticent. This is not the program to do that. This is a program that's, I think, a really democratizing force within NSF to pull people in from all walks of life and different types of expertise. You know, and you probably need less time to prepare for it than you would think if you haven't done this before. So I'll stop there and yield my time.
Stephanie or Arindam, lessons?
Yeah. I submitted my first year. I also don't know really why I did that looking back. But I, you know, thought I had an idea that I loved and wanted to just go forward and do it. Probably a little bit of pressure from up above. But in between, then in my second try, there were 2 years. And so I submitted again in my third year. And I feel like from then on, I just kept working towards what I thought the idea was. And so eventually when it came time to really start writing, which I probably started like 3-4 months before really writing. And I still would say like that could even be too late. You can never start too early on this proposal. I think from then, everything that I had done allowed me to like really build up some preliminary results that supported all of my ideas. So it wasn't necessarily that I was already doing the work, but that I could kind of shape things a little bit more concretely than the first time around by just continuing to put work into the idea.
Thank you, Stephanie. Arindam, do you want to share your lessons learned since you submitted a couple of times before being successful?
Yeah, sure. One thing that, if you read the solicitation carefully, it kind of says this should include the activities pursued by an early career faculty to build a firm foundation for a lifetime of leadership in integrating education and research. It's kind of in line with what Forrest, Stephanie, and Elena just mentioned. So I think, as I mentioned, I mean, in the first 2 times, I didn't do probably a good job in that integration. I was focusing on research. And the other component that is missing is the assessment part, because you have to have a mechanism of assessment of your research and educational outcomes. And if things are not going the right way, then you have to intervene and you have to change the course. So the assessment is very needed part, which I kind of neglected. The other thing, if you read the solicitation, again, it will say that these plans should reflect the proposer's own disciplinary and educational interests and goals, as well as the needs and context of his or her organization. It's a very important line if you read that in the solicitation. So you have to also kind of see, like, in addition to your career goals, where is in your university headed, right? Do they have any strategic goals or something that you can bring in the context of your career? So these are the important things that I kind of missed in the first 2 times. So if I may just say so, when I did my first submission, the comments were kind of, first thing they said, like, you know, it's a long list of things I wanted to do, and any one of these tasks is an entire career proposal by itself. So they didn't believe in me that I'm going to do all of that. Then they said, like, all these activities that you're trying to say that you have integrated the research and education look like bolt-ons, because these are not really integrated, but rather than you're just bolting them on without a purpose. So I thought, and then again, I revised and I proposed for the second time. And again, the integration of the research and education was not very good. And also they said that, again, I'm proposing like too many things. So it's important to kind of have a realistic tasks list, because as other 3 people said, like, this is not just about your 5 years. This is for your entire career, or probably at least your 15, 20 years down the road, right? So you don't have to put everything that, and it's not possible to do everything in 5 years. So you can say that this is my big goal and I want to reach there in 15 or 20 years, but in the first 5 years, this is what I'm going to do, which is an important step to reach the ultimate goal that you have in 10 or 15 years. So that will become believable. So I did that in my 3rd proposal. And I also learned from a workshop by a brilliant guy who taught me how to integrate the research with education. And for that, I literally read for 6 months, probably 60, 70 educational journals. And I knew that, okay, there is a really educational need for undergrads who are not graduating in the real time. And right now in our college, 6-year graduation rate and 4-year graduation rate are the big 2 things that people want to tackle, from the provost to the president. So it's relevant. So I kind of put it into the relevance of my university. And then when I integrated everything and put a realistic kind of task list, which doesn't look like it's too much, then the 3rd time, I got like very good reviews, like 3 excellent, 1 very good, and my proposal was funded. So those are the things that I learned from the first 2 submissions, I'd say.
Thank you, Arindam. And I'm sorry, I've been having Forrest's picture up for a long time. There was a question that was submitted, and I wanted to put it up here. And then we have some more that are coming in through the chat box. But what recommendations would you give to doctoral students? So we have some doctoral students that are on the call now that are nearing, what advice would you give to doctoral students that are nearing graduation in preparing a research plan and generating evaluating proposal ideas?
I can offer maybe two pieces of advice to this crowd, and I think to early stage assistants as well. The first, I think, when you're a student, you're in this position where you're sort of taking orders from somebody, and you're trying to figure it all out. But very soon you're going to be a professor, and then you're going to be that person. And so it's very natural to, when you first start, to carry some insecurity, and that kind of propagates into your writing. But you need to move through that very quickly. You really need to learn how to write in a confident tone. It's what often happens is, and specifically if you want to look this up, you need to learn how to write in an indicative mood. Indicative mood, that's the proper way to describe that. But that'll help significantly with how you pose your questions. You don't want to be wishy-washy. A career proposal, or any proposal really, I don't, if I'm reviewing something, I don't want to read that someone hopes or aims or wishes to do something. I want them to speak with some confidence about what they're going to accomplish. And a big part of this too is, as you develop this, is you really do have to exercise concision, and you have to learn how to write clear and explicitly. And when you tend not to have that confidence, it doesn't come across this way. It's like that the quote from Mark Twain. I didn't have time to write a short letter, so I wrote a long one instead. And this is often very true with people that are first getting started. They feel like they have to explain a lot. And they don't really know where to dial it in, and to give the reviewer some credit to, to figure it out. And that's something you need to try to work through. The second piece of advice I'd give you guys would be, if you're not doing it already, build your network. And in this day and age, it's very hard for faculty to do stuff on their own. And granted, this is a sole PI proposal, but this is why the NHERI program exists, for example, right? We have these tremendous resources and people to tap into, and it's important to reach out. And, please don't ever have the impression that somehow you're not needed or you're less important. That's just not how it works. I mean, federal agencies, all of them have programs like this to bring new people in, because, you're the lifeblood, you've got the new ideas. And so, shake any concerns you may have off, and dive right in, roll up your sleeves, and, and offer to work with people, to collaborate with people, attend these workshops that we'll have hopefully in person again. And, just know that there's a whole group of people like us, waiting to have you with us and help you, figure all this out.
Yeah, I think that's fantastic for us. I wish I'd have talked to you on day one of starting it as an assistant professor. Yeah, I think that's awesome. And I'll just share two other pieces of advice that kind of came to my mind when I read this question, and that's, make sure that you've covered your literature, right? And so if you wrote a dissertation, you should have had a really good literature review chapter in there, but just making sure you understand what all work has already been done, because I think that that's where, when I've had conversations or sat on review panels, it's like, oh, well, this was a new idea to you, but not necessarily a new idea. And so, but that's a solvable problem, because, you're covering the literature in your field. And by doing that, though, you'll be able to craft a much better argument about why your original ideas are so much better needed, or are needed, and be able to do that so much better. So I would just, first is just make sure you've covered the literature. And second, don't try to hide the limitations. Any work that you propose to do is going to have limitations. There's going to be assumptions. There's going to be shortcomings. You can't address every single issue and limitation in a single project. And so don't hide from those, or don't try to hide those from the reviewer either, because they're going to be looking for those too. What is it about your method that doesn't fit this problem perfectly? And so I think you want to make sure that you can articulate like where the limitations are, and why it's still going to be okay, why what you're proposing is still a great approach, and why perhaps in your career those limitations lead you into future work after the 5 years. Yeah.
I would add one more, maybe super practical thing would be, if you haven't already, ask your advisor if you can help write a proposal. Most of us are engineers, so learning by doing is super helpful.
you want me to add something, Karina?
If you'd like, Arinda, you don't have to.
Okay. No, I think my advice would be, I think it's again, learning by doing means like you have the opportunity right now for students who are nearing graduation to read the recently funded NSF proposals, at least the abstracts that are available on the NSF Award website. So you can develop an idea of what kind of ideas or what kind of proposals are funded. I think it's important to understand that. That will make sure that you are thinking in the right track. That would be one piece of advice which you can do starting today. Networking, as Forrest mentioned, is extremely important, though it's not a collaborative kind of proposal, but you can obtain letters of collaboration for a few things that will be needed for your career proposal. So that's very important. And then try to be, in this ever-changing world, try to be better learners than just being better learned, okay? Because things are changing. You have to be adaptable to many things. And most of your career, if you become a faculty now, you have to focus on mostly multidisciplinary, transdisciplinary, those kind of things. It's not just focusing on one area, may not be very much applicable in this age, basically. So you have to develop that mindset, how to think broadly, how to be adaptable as you go and pick up various new things that are coming. As of now, I mean, for example, I had no idea about machine learning, but now Stephanie is giving me some lessons on machine learning and I'm open to it. I want to learn, right? 5 years back, I had no idea. So you need to have that open mind. So you have the opportunity of collaborate on a bigger thing, because that's where we are headed with the multidisciplinary research. So those will be my thoughts on what you can do right away and what would be valuable.
Thank you, Arinda. I'm going to put this up just for your information while I ask the next questions, and these have come in through the chat box. Did any of you apply for an unsolicited proposal before going for a career proposal?
Yeah, I was funded. I had at least 2 or 3 NSF awards already before I got my career. And that's another issue that could be, so it's a double-edged sword, right? If you have some experience, that's good. But then if you have many hours, then people will say, oh, it's kind of repetitive. I mean, what else he wants to do, right? So you have to make sure that your career proposal has very clearly stated objectives, which builds on your previous research or awards, but it's not overlapping. Okay, so I think that's extremely important. And then the way I try to do it is, from my previous awards, I use some of the preliminary data as an input to the career proposal. So I put some of the graphs from my other research and say, hey, these are the evidences that my hypothesis, there is a great chance that it will be right because of I have these preliminary data. So it's very important to also work on getting some preliminary data that can support your career proposal so things look believable. So yes, I had awards before career.
So where I was able to get the career proposal funded after one try, I had probably tried, I mean, if you looked at my Fastlane account, I had probably submitted 8 other proposals to NSF and they were all rejected by the time I submitted my career proposal. So certainly some of them were unsolicited. I know there was a rapid in there. At the time, let's see, at the time that this proposal went in July, I ended up getting a couple other proposals that came through during that same kind of review cycle. But leading into this proposal going in, I had not received other funding from the NSF, but had definitely tried.
Yeah, I was less lucky than both of you. And I had submitted a number of different unsolicited proposals and none of them were funded.
I had one project with NSF then, which was the NSF PATH program, which coincidentally, random, that was the first Wall of Wind NSF project that
I still remember that, Forrest. Yes, that's for the PATH program. Yes.
So the next question is, was there a single person who you communicated the most to get feedback?
I communicated with many, of course. Yeah. So I think I definitely talked to my colleagues like Forrest and other people. And then I formed 2 internal committees, and this was again advised by my consultant. So I had one committee who were kind of technical people, and then one committee who were kind of from other areas. Okay. And then I also talked to a person, Hilary Landorf, doctor, and she is an educationist at FIU, and she kind of is the head of Global Learning for Global Citizenship program. And I talked to her about the education, about the assessment, and finally I included her in the proposal as an assessment consultant. And I kind of put like $5,000 per year for her evaluation of my thing. So I think the reason for this is I wanted to get feedback of not only the technical people in my area, but other people in other areas, so that they can tell us like what makes sense and what from an outside person is recommended, or the paths that are not very clear. So I got input from various other people, and that kind of improved my proposal a lot. So the comments that would have been given by the reviewers were already tackled because they gave me the comments, and I kind of addressed those things. So that's what I did. And so it's very important that you have your proposal reviewed by, I don't know, 5 to 6 people, so that you get feedback and you incorporate those comments before actually submit the proposal.
So if I can add to that, and probably something we should have all said very early on, it's important for all of you to understand that there isn't a one-size-fits-all approach. Some of you really can benefit from what that the term of art for that, it's called a red team review. Color teaming is something that's used in basically federal contract acquisition. So big companies say like Lockheed and others use methods like this, and you have different colors of teams for different stages of a proposal review. But a red team can be very helpful for some people for a couple of reasons. One, the way it works is someone will get each person gets the proposal and reviews it, but then they get together and they talk. And that's where the really interesting stuff gets sussed out. And that can be brought back to you with some corrective actions. But probably the most important thing about that type of red team that Arunam's talking about is you have to understand that you're not writing to yourself. And a lot of people make this mistake. In fact, often when you meet, even full professors, or probably more like associate professors, they can't get to full. They get really stuck because they never learn that lesson, that how to speak to their audience. In the case of career, you could have a pretty diverse group of people, looking at your proposal. And if you talk past them, you write for yourself, it's really going to hang you up. And so it's very important to get this stuff out, because you're not going to understand this on your own. You're not going to see it, and what they can help you do is like really understand what they don't like. You can begin to understand where you're invoking biases in the reviewer. And this can happen many manifold different ways. But these nuances kind of get brought out, and it's really important because the competition is so stiff. And arithmetically, it's you look at all the reviews, and one good or one fair can most likely be the end of it for you. So the way you really should look at this is probably not where you'd first start. You probably think to yourself, I want to do everything I can to maximize the likelihood I'm going to win. But especially when you get started, try to think of it a little bit differently. try to minimize the likelihood that you're going to fail at this. And that means debugging your process. And you need to be super careful, particularly in the higher education business. It's the funniest thing. Even though we're in the knowledge business, we do a really lousy job of putting continuous improvement processes in place. So you heard a couple people touch on this. You have to look at this as a learning experience. You're gonna learn about yourself. You're gonna learn about how to communicate, and you're really gonna, learn how to make a, a pitch perfect explanation about what you want to do that can reach, people that aren't like you, that people don't come from the same disciplines. So, maybe you're one of those amazing people that never had to work in a study group in college and could do everything by yourself. There are people like that in the proposal world, but they're very, very rare. Almost everybody needs somebody. And in my case, back then it was Kurt Gurley, who's actually on the call today, who was my advisor at one point and later a colleague. So thanks, Kurt. I owe you one.
Yeah, I would add to that, it can be super daunting, especially if you don't get started early enough, to think about sending your proposal out to a bunch of people and getting all that feedback at once. I agree that it's super valuable. One thing you can do is send pieces to certain people. So like I think it's probably better in this case specifically to send the whole thing, because everything should really tie together. And so that helps to get the idea. But some people, will offer to read a couple of sections and not be able to read the whole thing. So like for instance, our education, my education component, our Center for Teaching Excellence, she, who was in charge there, offered to read just the education plan. And, if that's what she's able to read, I'm willing to give her that section. And that allowed me to at least get some feedback rather than the whole thing. And yeah, just finding someone who is technical, who has some of the education components, someone who has some experience in the program that you're writing in. All of those things allow you to get, like, if you can get someone to read your proposal. More so though, I just kind of talked about my idea to anyone who would listen. So if people may not have the time to read your entire proposal, you can still, in experiences like this, when I was there in person last year, I'm sure I talked to people's ears off about what my idea was. At every workshop I went to, I understand that now it's a little bit harder with the virtual circumstances, but just kind of anytime you can get on a call with a colleague or, somebody at a different university, somebody at NSF, whoever, if someone was willing to listen to me for 5 minutes, I probably talked their ear off about this idea, and I was able to get a lot of feedback that way.
Yeah, I'll just add on to that briefly too. There was definitely no one single person who I talked to the most, or by any means. And I took I think a more similar approach to Stephanie too, in that I really didn't send the written document or even portions of the written document to very many people at all. But I had lots of conversations. And part of that too was me strengthening my argument and how I was presenting the idea too, because, if I couldn't say it in a compelling way, then that, then I needed to go rework my argument, rework the way that I was phrasing it. And then the way that it would come off to that different person I was talking to is like what Forrest was getting at about the biases and whatever assumptions I had built in about the person who I was talking to or the reviewer on a panel. So yeah, I had as many conversations as I possibly could. And as Stephanie was getting at, that's obviously, you're challenged by that right now because we're not doing professional travel. You're not seeing all these people in person that you could go up and ask for a 5-minute conversation. So instead you're kind of, you might be in the position where you need to be reaching out online via email to people. And so I just want to encourage you that, of course, people are busy, and that it's really, I think it's intimidating to reach out to people and ask for help like that, but you need to just let that barrier down and do it, and really reach out for help, reach out for that advice, ask for that 15-minute phone call or what have you, ask for that email feedback, whatever it is, and don't shy away, because the people who will get the awards are the ones who didn't shy away for asking for that feedback. So don't let that be you.
If I can just add to that really quickly, this is all great advice. It is important though who you ask, like thinking about that and making sure you're getting to the right people, because there's certainly, almost everybody will give advice in this profession. but there's really a subset of the people that you want to hear from. And there's also the subset who means well, but ultimately is trying to mold the younger generation like them. And you should try to avoid them at all costs, because the way this business really works, what's our real strength is our diversity of our thought and our backgrounds and the way we see the world. And I've been in this position before where I'm mentoring junior faculty, and I come across this situation, and the best advice I can give them is you need to listen to yourself, right? You've got to be you got to be the best version of you. So as you're going through this, you may get some good advice, but you're going to get the good and the bad with this. And try to build intuition about receiving this information, how you're going to use it, because there are lots of great people that want to tell you great things, but it may not be the right fit for you. You probably have mostly a good experience. Please don't avoid asking people for help based on what I'm saying here. Okay, I hope you get my point.
If I just want to add to that, yeah, I think getting the right people for the advice is really important. So when I said I sent my proposals, I didn't just send it just one fine morning. I kind of chose okay, these are the 4 people that maybe are good in all the respect, and I trust them. And I went to them and I said this is what I want to do. Would you be agreeable to review this? And then once they said yes, then of course I will send it, because I have to make sure that the people I'm sending my 15 pages, which is, and a lot of hard work and a lot of ideas, they are the right people and they will give me the right feedback. But again, as Forrest said, I think it's important, you're going to get a lot of things and you have to weed out which are applicable to me and which are maybe not. And I think the intuition is a great asset that we all have. And the more we have, the better we are. So that's an important tool.
Thank you for your advice. That's very helpful. And I do think that it's important to listen to yourself. So that's good advice. So we have another question about the number of collaboration letters. So how many letters of collaboration did you submit as part of your application is the question.
I had about 4 or 5, mostly from the educational part. And again, that's a very important topic. And I think I still haven't learned the whole thing, but the reviewers and the program director, they can see through somehow, I don't know exactly how, which one are real collaborators and which one you are just putting there to make your proposal look good. Okay. So you have to make sure that when you ask for a collaborative letter, it's something that really enhances your proposal and you're going to really collaborate. It's just not that look good kind of thing, right? And right now the collaborative letters are just one line, but that's why it's more important that in your project description or facilities and document, you have to kind of mention exactly how that collaborator is going to be beneficial to your proposal. Because if that's not convincing, then the collaborative letter hurts your proposal more than it does anything good. So just keep that in mind when you think about collaboration.
So just to make a really important point. So, these letters, they're not there for aesthetics. They're there, they have a structural purpose, okay? So the way you're gonna use this, you're gonna develop a narrative. You're gonna tell the reviewer, this is what I'm going to do. And then parenthetically, you're gonna say, see the letter. Or remember, with the career award, like most NSF awards, cost sharing is disallowed, right? So that, it levels the playing field for everybody. But in the facilities, equipment, and other resources page, you can talk about what you have on hand. That addresses one of the merit criteria. And so you might find yourself, hey, I want to use this facility. And that's where you could talk about that other person and you could reference the letter. So that's how that's done in terms of how you put these things together.
Yeah, I had on the order of 8 or 9 letters. I had, of course, it's not a letter of collaboration, but it's more of like a letter of recommendation or a letter of agreement from my department chair. And then I had a letter from my letter of collaboration for the Center for Teaching Excellence at KU, a letter of collaboration from the SIM Center PI, so that it was clear that I had talked to the SIM Center about how I wanted to use them in this proposal. And then the other letters, so about 6 or so, were an advisory board. And Arindam is so right too. Reviewers can see through letters that are added on there just for fluff. And that's what my reviewers called out, that, you know, they were like, we can tell that this advisory board is not gonna be the types of people who sit on the sidelines. And so, I mean, that was called out in my reviews. And so, but my advisory board, I don't know that that's particularly common. I did it with big intention, and that's that my proposal was really multidisciplinary, just like what everyone's talking about too, about moving into that multidisciplinary space. And so as a structural engineering professor, I was talking about applying sociology and anthropology and urban planning and wind engineering and earth engineering theories and principles. And so how on earth could I, at 3 years into my, you know, career or post-PhD career, be able to be an expert on all of these different topics, right? And so, like, I can't possibly be an expert on all of those topics. And so that was the way that I presented my advisory board. Is so that's who all of those expertise were, as well as an educational expert, to show that all of, you know, these limitations, I'm going to make sure I've got key players in place who have that as their core expertise to help make sure that I stay in line from those different perspectives. But it was also strategic such that my wind engineering expert, for example, he's in practice, and he's the chair of the Infrastructure Resilience Division, or he was at the time, of ASCE. So it was, you know, when I talk about moving my work into practice too, in that translational aspect of the research, there were people in practice who were in those key leadership positions on my advisory board too, that could help demonstrate how I was going to make that achievable. And so I wasn't just waving a wand and saying, now practice will adopt it, but I had those key players on my advisory board with those varying expertise too. So I think the letters were critical for me, especially with such a multidisciplinary project proposed.
Karina, can I add something?
Go ahead.
Sure.
Of course.
I think one of the things that is I found out to be very helpful, and it was not for my career, this was for an MRI award that we got, for which we had a record number of 25 letters of collaboration, right? So why I mention this, because I think it's important to reach out to these collaborators very early in the stage and discuss with them, what's the plan? Would they be able to help you in the way that you want? So for the MRI, what we did, we were asking for a piece of instrumentation. So we knew that these will be the users, but we asked, we wrote something like a paragraph, but on how they can use the research, but then we sent them and said, look at this and revise and edit, add as you feel appropriate. So they had their input from the very beginning. And when I plugged those things in the project description, it seemed very realistic. It didn't seem that I'm writing something for someone, but it's as if they are writing that, right? So I think it's applicable for the career award in the sense, let's say you have a collaborator and you identify that person very early stage, you talk to that person and you share the idea of the collaboration, and whatever you're going to put in your project description, it will be good to send him or her that paragraph and say, this is this kind of, you know, puts out what we talked and we are okay. And then when that person edits and reviews and put his or her things in that and you plug it back, I think it looks much more realistic as a collaborator and not just as you're writing something and you have no clue like if this is going to be done or not. So I think this kind of reaching out to these collaborators early and getting them involved in the planning is an extremely helpful thing for your proposals.
Thank you, Arvinda. We have another question about pursuing a different area. If you're interested in pursuing research in a new area or topic than what your background is in, how do you go about making sure you have an adequate background and technical knowledge other than reading papers?
Difficult question, but I'll try to answer, and then I need help from Elina, Stephanie, and Forrest. Just going back to what I said before, as of now, I don't think focusing just on a narrow subject is any longer relevant to the science that we are pursuing, right? So we have to be a lifelong learner, and we have to pick up on new things that are coming in which we are interested. So I think one of the advantage that we didn't have, at least Forrest and I didn't have, but other people they have, is the Nihiri was not there, right? We didn't get a support of the Nihiri. We didn't know all these faculty who are ready to help, all these facilities and sim center and everything that you can leverage. We didn't have that. So now I think it's easier to go into a different area rather than your very specific one that you did PhD on, right? So I think you should solicit your help from the Nihiri network because you have all the expertise of every natural hazards here. So you have a lot of resources, both like resources in terms of infrastructure and resources in terms of personnel. So you should make use of that. And then if you're trying to delve in a new area and you want that to be your career proposal, it's always good to have some preliminary conference publications and things like that, and preliminary data that you can put in your proposal to make sure that the reviewers understand that, yes, this is kind of a new area, but you have some kind of expertise and you have some kind of preliminary data that makes, again, your proposal more believable, okay? So I'd say that those are the two pieces of advice. Use Nihiri as best as you can and develop some preliminary data and some basic, at least some conference proposals, which you can put on your bias sketch. So they know that you have some knowledge in this new field.
So, Elena, are you going to jump in?
Yeah, but you can go ahead.
No, go ahead.
I was going to say just quickly too that, yeah, one of the beautiful things about NHERI is really design safe, converge, right? Is that, and within converge is steer and gear and ICEER and SEER. And so all of these extreme events reconnaissance platforms, right? And so whatever it is, if it's within the bounds of NHERI, there is some example of data published on Design Safe that you can access, right? And you can start learning from. And there is sadly extreme events occurring year round. So you can join one of those reconnaissance teams. And so that's a great way for you to network and a great way to do what Arindam was saying of getting something on your CV, get you that initial exposure into that hazard or into that disciplinary space. And so just don't forget to take advantage of the important resources that the NSF has provided to you through NHERI.
And just to support you, support that, I think Elina and we worked together on such a topic that the data was from another project uploaded on Design Safe, and Elina used it, and her student was brilliant, and we submitted a paper which hopefully is going to publish. So it clearly shows like how that is possible, how you can reuse some of the data and delve into an area that you want to and make it credible at the same time.
Absolutely.
So unless you're talking about jumping from cement to mortar, good for you, okay? We need more of that, frankly. If you look at the state of science and technology, the fields are homogenizing at an unprecedented rate right now. for those of you that just came out, you know, you joined a profession when things are just highly dynamic. We're in this period of accelerating change, right? And artificial intelligence, automation, the combination of those two things is fundamentally changing how we do research. The investigative power of a single researcher is going to increase tenfold, 100-fold, 1,000-fold in the next 10 years. So, you know, I think in 20, 30 years, we're not going to be educating sort of these disciplinary, you know, specialists, right? They're going to have to be sort of these T-shaped engineers. They're going to have to be polymaths. So anything you can do to, you know, broaden your understanding of the world and the skill set you have, all the better. Now, that being said, I gave some pretty practical tips, you know, going in blind. Obviously, doing the research is really key, right? I mean, you need to go in, you need to look into the literature, establish a basis. Also, this is where all the talking comes in, the communication, the networking. You know, you got to have a few aunts and uncles in the business. They're going to point you in the right direction and tell you that's great or that's stupid or that's never going to work, right? And kind of pull you back in. And at this stage, when you're when you're brand new, this is a great time because people give you really honest feedback. That changed a lot when you get to be kind of seasoned a bit. You don't get that as much, right? And so, you know, embrace that. Encourage people to, you know, really give you candid advice on what you're trying to do. And also just keep in mind, specifically the Career Award. Career Award is not a research award. It's a career development award, okay? This is the jumping off place for the rest of your career. And you can build a strong narrative around that about augmenting what you're going to do. You know, when I was in college, when I was finishing up, I was doing, you know, stochastic mechanics stuff with Kurt and some limited storm chasing stuff, field work. I never did like lab testing. That's all I do now. You know, things are going to change. And, you know, our predecessors and before them, you know, they had the advantage of when they were trained that they could probably do it for 40 more years. You guys don't have that advantage. You know, the knowledge is growing so quickly. The tools are growing so quickly. It's never been a better time to try to do some new things. So I applaud that, but be intelligent about how you make your claims and you set yourself up to do that. Rely on the people around you to do that optimally.
Yeah, I kind of think the answer is in everything that we've been saying through the whole time. Like, you're making a story with this proposal. You're telling a story about your success and like your future success and the potential that you have. And so all of these things like the networking and the work integrating of the different plants, everything that's going to tell a story of how you are the right person to do this job. And so it might mean that you can kind of leverage what your past experience is, but ultimately you're talking about why you can do something that nobody else can do. And so then I kind of think it plays back into what Forrest said in the very beginning about just being confident and writing in a confident manner. And that in itself will help you to stand out as somebody who can be the person to do something that no one else has done.
And if I may just add to that, I think whether you're shifting from this subject to that subject or coming up with a different line, you have to always understand that it's not only the intellectual merit, but you have to make sure the broader impact is there in the proposal, right? So the first thing about the broader impact is what is the societal benefit? And again, that's where you will have an advantage because, as Elena mentioned, like Dr. Laurie Peake's Converge program is something where you can kind of relate any engineering thing to the social science. And I think you should take advantage of that and make sure that wherever you're going, ultimately it's providing a benefit to the society and making our lives better, making the citizens, you know, safer or with more resources, more resilient or whatever. So take advantage of that and tie into the broader impact of whatever field you're going to pursue.
Thank you. Thank you to all of you for your advice and your sharing your experiences, which I think is very important. We've come to the time. It's 5:30, so I want to be respectful of the time. But I do, before we leave, want to acknowledge all of our panelists for your help in providing this knowledge to our audience. So thank you all for each piece of advice. And we hope that everyone on this call will be happy. I've already heard some feedback from folks, but happy about the information that you received. You can connect with any of the sites tomorrow. If you weren't able to get into the Google Docs, you can send me an email directly and I will forward that to the site representative. And then thank you for participating. You are part of the NHERI network, so please log in, go to Design Safe, create an account, and our communications. You can receive emails and information that way. I just got a message that my internet is unstable, so it's I think it's time for me to call it. But again, thank you all, and you're seeing a lot of thank yous on the chat box from the audience. So your participation is much appreciated from the panel. Thank you, Joy, as well for all your help.
Thank you. This was great. And this was a great panel. So I think, hopefully, I think a lot of great information was provided to everyone today. So thank you all.
Yes, thank you. Thank you so much. We cannot do this without you.
Exactly, yeah. I think we should all be thankful to Dr. Poshki for the Nihiri program, because again, I will reiterate that Forrest and I didn't have this advantage when we submitted our career. And now the resources you have is amazing. And thank NSF for that.
Yes, thank you.
All right, go get them, guys.
And with that, we'll go ahead and close off. Thank you all for coming.
Good luck.
Thank you.
Yeah.